Settle down, let your body sink into wherever you are resting, loosen the jaw, let your eyes grow heavy. Tonight, we are not rushing. Tonight, we are drifting. Drifting backwards through time. Back, far, far beyond the first humans, beyond the dinosaurs, beyond even the first single-celled life. We drift billions of years back, to a time when there was no Earth at all, only a cloud, only starlight and silence. Close your eyes if you like, and picture a vast, endless space. The Milky Way young and restless, filled with swirls of cosmic dust and scattered gas. The universe itself had already been alive for nearly 10 billion years. Stars had come and gone, blazing with light, exploding into fragments, scattering the seeds of new worlds. Among those seeds were the building blocks that would, one quiet day, become Earth. But in this beginning, there was no planet here. No soil, no sky, no ocean, only drifting particles, lighter than a whisper, spread across a wide spiral arm of our galaxy. These particles were ancient. They were the ashes of dying stars, atoms of carbon, oxygen, silicon, iron, born in furnaces that had burned long before our sun even flickered into life. Imagine these particles like a mist, filling the darkness. Imagine that they are patient. They wait, and slowly they move, drawn not by any sound but by the quiet pull of gravity, the soft hand that gathers all things together. Gravity is gentle, but it never rests. Over millions of years, the mist began to swirl. Dust joined dust. Tiny grains clumped together, sticking through delicate static charges, the same way lint clings to fabric, and as they joined, they grew heavier. Pebbles formed. Pebbles became boulders, and the boulders began to dance around a newborn star. Our sun had just ignited, a brilliant heart of light in the middle of that swirling cloud. Nuclear fire lit up its core, and for the first time in that corner of the galaxy, day had been born. Around this sun, a disk of matter whirled. This was the solar nebula, a spinning platter of dust and gas, shimmering, glowing faintly in the star's warmth. In this spinning disk, some patches of dust grew faster than others. Their gravity pulled more and more material in. You can picture them as little whirlpools, each tugging, each claiming its share of matter. Dozens of them formed, the seeds of future planets. One of those whirlpools, not too far from the sun and not too close, began to grow larger. It was here that Earth's story would begin. Take a deep breath. Hold it for a moment. Feel the air filling your lungs, the gentle rise of your chest, the quiet rhythm of your body at work. Now breathe out, slowly, and as you do, consider this: the oxygen you just released, the carbon dioxide leaving your lips, the very atoms that make up your breath. They are ancient beyond measure. They are older than mountains, older than oceans, older than the Earth itself. Every atom in your body, the oxygen that fuels your cells, the calcium that gives strength to your bones, the iron flowing red through your veins, the carbon that forms the backbone of every molecule of life within you, all of it, every single piece, once drifted in the cold darkness of space. You are not separate from the cosmos. You are a piece of this story, a chapter written in flesh and bone, carried across billions of years from the heart of dying stars to this moment. Here, now, reading these words. Before there was Earth, before there was a sun to warm it, before there were planets or moons, or the gentle pull of gravity shaping worlds, there was only a cloud. Imagine it, a vast, silent nebula, stretching for light years in every direction, a cosmic fog of gas and dust suspended in the void. It was dark, so dark that no human eye could have seen it. Yet it was not empty. Within that darkness, hydrogen atoms drifted, helium gathered in wisps, and scattered among them were heavier elements: carbon, oxygen, nitrogen, iron, silicon, all forged in the nuclear furnaces of ancient stars that had lived, burned, and died long before our story began. These stars, giants compared to our sun, had spent millions of years fusing lighter elements into heavier ones, building the periodic table atom by atom in their blazing cores. And when their fuel ran out, when they could no longer hold back the crushing weight of their own gravity, they collapsed inward in a catastrophic instant, then exploded outward in supernovae so bright they could outshine entire galaxies. In those explosions, the final, heaviest elements were created. Gold, uranium, lead, and all of it, the entire chemical heritage of those dead stars, was hurled into space, seeding the cosmos with the raw materials for new worlds. Our nebula, the cloud from which Earth would one day form, was made of this stardust. It drifted for eons, perhaps for hundreds of millions of years, slowly rotating, slowly cooling, seemingly eternal in its stillness. But nothing in the universe is truly still. Gravity, patient and relentless, was already at work. The first stirrings. Something disturbed the cloud. Perhaps it was the shockwave from another supernova rippling through space like a stone thrown into a pond. Perhaps it was the gravitational tug of a passing star, pulling at the edges of the nebula, or perhaps it was simply time, the slow accumulation of tiny imbalances that finally reached a tipping point. Whatever the cause, the result was transformation. The cloud began to collapse, not all at once, not uniformly, but in pockets, in swirls, in regions where the density was just slightly higher than elsewhere. Gravity pulled matter inward, and as matter gathered, gravity grew stronger. The more mass that collected, the more it attracted, a feedback loop that accelerated with each passing millennium. In the center of the collapsing cloud, pressure began to build. Atoms that had drifted peacefully for eons were now pressed together, colliding with increasing frequency and force. The temperature rose, slowly at first, then faster. What had been a cold cloud of gas was becoming something else, something warmer, something more compact. The center glowed faintly at first, then brighter, as gravitational energy converted into heat. Around this growing core, the rest of the cloud continued to spiral inward. But not everything fell straight down. The cloud had been rotating ever so slightly, and as it collapsed, that rotation accelerated, like a figure skater pulling in their arms to spin faster. The result was not a sphere, but a disk, a flat, spinning pancake of gas and dust, with the proto-sun blazing at its heart. This disk, this protoplanetary disk, was the nursery of worlds. It stretched for billions of miles, far beyond where any planet would eventually orbit, and within it, countless particles collided, stuck together, broke apart, and collided again. The process was random, chaotic, violent, and yet from this chaos, order would emerge. The dance of dust. Now zoom in. Imagine yourself floating in that disk, watching the dance of matter unfold around you. The particles you see are tiny, smaller than grains of sand, many of them no bigger than smoke, but they are everywhere, countless trillions of them, filling the space around the young sun with a haze so thick it blocks out the stars beyond. Feel the stillness of this place, a stillness that deceives. Though the space seems peaceful, almost serene in its dusty glow, everything here is in motion. Every particle, every grain, every fragment of stone and ice traces an invisible path through the darkness. They spiral endlessly around the infant sun, bound by gravity's patient grip, each following its own orbital rhythm like notes in a cosmic symphony that plays without sound. The disk itself stretches for billions of kilometers, a vast plain of matter so thin in places you could pass through it without noticing, yet so dense in others that the sunlight dims to a murky twilight. Near the center, close to the blazing heart of the young sun, the temperature soars high enough to melt rock, to vaporize metals. Here, Only the toughest materials survive: grains of iron, particles of silicate, fragments that can withstand the stellar furnace. But farther out, where you float now, the cold of space begins to dominate. Ice crystals glitter alongside the dust, water frozen solid, methane, ammonia, all the volatile compounds that will one day fill the atmospheres and oceans of distant worlds. Look closer at a single particle. It is irregular, jagged, perhaps 1/10 of a millimeter across. Its surface is rough, pitted by radiation, scarred by previous collisions. Under a microscope, if you had one here in this impossible place, you would see that it is made of many materials fused together: silicates rich in oxygen and silicon, grains of metallic iron, perhaps a coating of carbon compounds left over from the molecular cloud. This single speck contains within it the ashes of ancient stars, elements forged in nuclear furnaces that burned out long before our sun was born. These particles are in constant motion, orbiting the sun at different speeds depending on their distance. Those closer to the center move faster, racing along their paths at tens of kilometers per second, driven by the sun's immense gravitational pull. Those farther out move slower, taking longer to complete each orbit, wandering through the outer reaches of the disk where the sun's influence weakens and the cold deepens, and where their paths intersect, where the geometry of their orbits brings them together. Collisions occur. The collisions are happening everywhere, constantly, millions upon millions per second throughout the disk. Most are gentle by cosmic standards, two particles brushing past each other, exchanging momentum, perhaps spinning off in slightly altered directions. The impacts release tiny amounts of energy, barely enough to warm the particles by a fraction of a degree. Some collisions are more violent, faster, the result of particles whose orbits crossed at steep angles. In these impacts, fragments break off, smaller pieces scattering into the disk, adding to the countless population of debris. Most of the time, when two particles collide, they simply bounce off each other, perhaps shattering into smaller fragments, perhaps continuing on unchanged. The laws of physics govern each encounter with perfect indifference. Momentum is conserved, energy is conserved, and the particles separate, continuing their endless orbits as if nothing had happened. But the disk remembers. Each collision, however small, alters the distribution of matter, shifts the balance, creates conditions for new interactions. But sometimes, just sometimes, they stick. It might be static electricity that holds them together, charges building up on the particles' surfaces as they rub against the thin gas of the disk, creating attractive forces strong enough to overcome the tendency to bounce apart. Or it might be the faint molecular forces between their surfaces, van der Waals forces, the same forces that make dust cling to a shelf or frost stick to a window, operating here across the vacuum of space. Or it might be that they hit at just the right angle, with just the right speed, so that instead of bouncing they merge, their kinetic energy absorbed in the deformation of their surfaces, in the compression of their materials, leaving them locked together. The exact mechanism varies. Sometimes it is one force, sometimes another, sometimes a combination. Nature is opportunistic, using whatever works in each particular moment. What matters is not how they stick, but that they do. Two particles, each with its own history, its own composition, its own trajectory, become one. That new particle, slightly larger now, slightly more massive, continues to orbit, and it collides with another. Whatever the mechanism, the result is growth. Two particles become one, that one collides with another, and now there are three grains fused together, a tiny aggregate, barely distinguishable from the millions of others nearby. Then 4 grains join, then dozens, then hundreds. The process is slow at first, agonizingly slow. A particle might orbit the sun 10,000 times before it encounters another that sticks. But the disk is patient, and time is abundant. The growing aggregates are fragile. A collision too hard will shatter them back into their component grains. A near pass by a larger object might tear them apart with tidal forces. They tumble through space, irregularly shaped, held together by forces barely stronger than a breath. Yet some survive. Some keep growing, adding more particles, becoming stronger, more resilient. Their increased mass gives them slightly more gravity, an almost negligible pull, but enough to begin influencing the trajectories of nearby dust. Over thousands of years, these clumps grow from dust grains to pebbles, from pebbles to rocks, from rocks to boulders. The transformation is not uniform. Some regions of the disk are denser, richer in material, and there the growth happens faster. Other regions are sparse, swept clean by the gravitational influence of larger bodies elsewhere, and there the particles remain small, isolated. But wherever matter concentrates, wherever the density rises above a critical threshold, growth accelerates. Watch one of these growing clumps. It started as two grains that happened to stick together 100,000 years ago. Now it is the size of a pebble, perhaps a centimeter across, composed of hundreds of thousands of individual particles compressed and fused together. Its surface is rough, covered in smaller grains that have stuck to it recently. As it orbits, it encounters more dust. Some particles it collects, adding to its mass. Others it deflects, sending them spiraling away into different orbits. The larger they become, the stronger their own gravity, and the more effectively they can sweep up material from their surroundings. This is the critical transition. Once an object grows large enough that its gravity becomes significant, the process changes. It is no longer just random sticking, no longer just particles bumping together by chance. Now it is gravitational accretion, a runaway process where mass begets mass, where the largest objects grow fastest, pulling in everything around them. What began as random sticking becomes gravitational accretion, a process that accelerates exponentially. A boulder-sized object might take 10,000 years to double its mass through random collisions, but once it grows to the size of a mountain, its gravity extends far enough to pull in material from a much larger volume, and it might double its mass in only 1,000 years, grow to the size of a small moon, and that doubling time drops to mere centuries. The rich get richer, the massive become more massive, and the disk begins to organize itself into a hierarchy of sizes. After perhaps 100,000 years, a duration that spans thousands of human lifetimes, yet is nothing in the life of a solar system, the first planetesimals form. These are the true building blocks of planets, irregular chunks of rock and ice ranging from a few hundred meters to a few kilometers across. They are not yet planets, not even close, but they are no longer just dust. They are solid objects, each with its own tiny gravitational field, each capable of altering the orbits of nearby material. The formation of the first planetesimals marks a threshold. The disk of dust has become a swarm of boulders. The scale of the dance has changed. Where once there were trillions of particles too small to see, now there are millions of objects large enough to cast shadows, large enough to have surfaces and interiors, large enough to be called worlds in miniature. Imagine one of these planetesimals. It is roughly spherical, though not perfectly so. Gravity is not yet strong enough to completely overcome the structural strength of rock. Its surface is pockmarked with craters, each one the scar of an impact, evidence of the endless bombardment it has endured since forming. Some craters are small, mere dimples. Others are vast, stretching across a significant fraction of the surface, where a collision nearly destroyed the entire planetesimal, but instead only blasted away a portion, leaving a deep gouge that will remain for eons. The surface is a mixture of different materials, layers of rock and ice deposited during different phases of growth. In some places, dark basaltic rock dominates, rich in iron and magnesium. In others, lighter-colored minerals, feldspars, quartz, create patches that catch what little light reaches here, and scattered throughout are veins of ice, water frozen harder than steel in the cold of space, mixed with frozen carbon dioxide, frozen ammonia, all the volatile compounds that boiled out of the inner disk, but survived here in the cooler reaches. It tumbles slowly through space, not yet massive enough to pull itself into a perfect sphere, still jagged and irregular. Its rotation is chaotic, the result of countless impacts from random directions, each adding or subtracting angular momentum in unpredictable ways. Sometimes it spins around one axis for a while, then a new impact changes the rotation, and it begins to tumble along a different axis entirely. There is no day and night here, not in any regular sense. The sun appears and disappears from view in irregular intervals as the planetesimal wheels through space. Ice and rock are mixed together throughout its interior. If you could slice this planetesimal in half and peer inside, you would see layers of different compositions, like the rings of a tree but far more irregular, recording the history of its growth. Each layer represents a period of accretion, a time when material of a particular composition happened to be abundant in this region of the disk. Near the center, the oldest material is compressed by the weight of everything above, squeezed until the individual grains have begun to fuse together, creating a denser, stronger core. If you could land on its surface, an impossible thought, yet humor the imagination, you would find it cold, far colder than any winter on Earth, far colder than the coldest reaches of Antarctica. The temperature here hovers around minus 200 degrees Celsius, cold enough that carbon dioxide is solid, cold enough that even nitrogen begins to freeze. The surface crunches beneath your imagined footsteps, ice and rock broken into a fine regolith by the constant pounding of smaller impacts. There is no air, no atmosphere. The planetesimal's gravity is far too weak to hold onto gases, any molecules that are released by impacts. Water vapor from melted ice, gases trapped in the rock, immediately escape into space, drifting away to join the thin haze of the disk. So the surface is exposed directly to vacuum, to radiation, to the raw conditions of space. It is airless, silent except for the occasional thud of another impact, a vibration that travels through the solid body but creates no sound in the absence of air. Above you, the sky is black but not empty. The sun glows, a fierce point of light, smaller than it appears from Earth, but still the brightest object in the sky. Around it, the disk stretches, a faint band of light created by the countless particles still orbiting, still colliding, still growing. You can see other planetesimals, dozens of them, scattered across the sky at various distances. Some are close enough to show a visible disk, irregular shapes silhouetted against the background glow. Others are mere points of light, distinguishable from stars only by their motion, the slow drift as they pursue their own orbits. But this planetesimal is not alone. The disk is full of them, thousands upon thousands, all orbiting the sun in a vast chaotic swarm. Each one is on its own journey, following its own elliptical path around the young star. Some orbits are nearly circular, smooth and predictable. Others are elongated, eccentric, taking the planetesimals far from the sun and then swinging them back in close approaches that warm their surfaces before they retreat again into the cold. And inevitably, their paths cross. Two orbits that were separate, isolated, begin to converge. Perhaps one planetesimal's orbit is slowly changing, perturbed by the gravitational influence of a larger body elsewhere in the disk. Perhaps both orbits are shifting, responding to the complex gravitational environment. Whatever the cause, they are approaching, their paths bending toward each other, and nothing can stop what is about to happen. The age of collisions. What happens next is a cosmic demolition derby that lasts for millions of years. Planetesimals collide constantly. The disk, once a realm of dust and pebbles, has become a shooting gallery of kilometer-sized objects moving at orbital velocities, speeds measured in kilometers per second, far faster than any bullet, fast enough that the kinetic energy involved in even a small collision is staggering. Some impacts are glancing blows, near misses where the two planetesimals clip each other with their edges, transferring momentum without directly colliding core to core. These encounters send both objects spinning off in new directions, their rotation rates changing, their orbits deflected into new paths. Fragments break off from the impact sites, pieces of crust torn away by the force, tumbling away into space to become small planetesimals in their own right, or to be swept up by other bodies. But the main masses remain largely intact, battered but surviving, continuing their journeys through the disk. Watch one such glancing collision. Two planetesimals approach each other, their paths converging at a shallow angle. One is roughly 3 kilometers across, dark and irregular. The other is smaller, perhaps 1 kilometer, brighter with surface ice. They are both moving at about 5 kilometers per second relative to each other. For hours before the collision, they grow closer, their mutual gravity beginning to bend their paths, pulling them together more directly than their original orbits would have taken them. The collision happens in slow motion on the cosmic scale, yet faster than an eye could follow if anyone were there to watch. The surfaces touch, rock meets ice. The contact point explodes, vaporized instantly by the energy of the impact. A spray of debris, fragments ranging from dust to boulder-sized chunks, erupts from both objects, expanding outward in a cone. The two planetesimals grind past each other, their surfaces tearing, scraping, each pulling at the other with tidal forces that raise temporary bulges in their shapes. Then they separate, spinning away in different directions. The larger planetesimal has lost perhaps 10% of its mass, a huge crater carved from its side exposing fresh interior material that glitters with ice crystals. The smaller one has been fractured, cracks spreading across its surface, but it holds together, wobbling as it tumbles, its rotation now wildly irregular. Both will continue to exist, to accrete more material over time, perhaps to collide with other objects. The debris field they created spreads slowly, a temporary cloud of fragments that will eventually be swept up by other planetesimals, or will slowly drift away. Other collisions are head-on, catastrophic, the worst-case scenario for any object in orbit. These happen when two planetesimals approach on nearly opposite paths, their orbits intersecting at a steep angle, or when one is in a highly elliptical orbit that brings it plunging down through the disk at high speed. In these impacts, the relative velocity can be enormous, 10, 15, even 20 kilometers per second. The kinetic energy is proportional to velocity squared, so a head-on collision releases far more energy than a glancing blow. Picture such a collision. Two planetesimals, each about 2 kilometers across, approaching each other directly. They are moving so fast that they close the final distance in less than a second. There is no time for gravity to significantly deflect their paths. They simply hit. The result is total destruction. The impact energy is so great that both objects are shattered completely, reduced to rubble in an instant. Rock that has been solid for 100,000 years is blasted back into fragments. The temperature at the impact point spikes briefly to thousands of degrees, hot enough to melt stone, to vaporize ice. A shock wave propagates through both planetesimals, faster than sound, a pressure wave so intense it cracks and crushes everything in its path. Both bodies essentially explode. Their fragments fly outward in all directions, an expanding cloud of debris. Some pieces are moving fast enough to escape the mutual gravity of the fragments entirely, shooting off into independent orbits around the Sun. Others are moving slower and will fall back, eventually reaggregating into new planetesimals over thousands of years. The collision has taken two objects and created thousands, a momentary reversal of the accretion process. This debris either disperses slowly, the fragments drifting apart over time until they are indistinguishable from the general population of small bodies in the disk, or slowly reaggregates into new planetesimals. Gravity never stops working. The fragments, though scattered, still orbit in roughly the same region of the disk. They encounter each other again, colliding at lower speeds now, and some stick together. Slowly, over millennia, new planetesimals form from the rubble, perhaps several smaller ones instead of the two larger bodies that existed before, or perhaps eventually one large one again, reformed from the ruins. But some collisions are neither deflections nor destructions. Some are mergers, the productive collisions that drive planetary growth. These happen when two planetesimals of similar size meet at a relatively low speed, low being relative, perhaps 1 or 2 kilometers per second rather than 5 or 10. At these velocities, the impact energy is enough to shatter the surfaces, to create craters, to melt some material, but not enough to blow both objects apart. Instead, they stick together. The collision creates a crater at the impact site, and both objects deform, their surfaces crumpling, fragments breaking off, but their combined gravity holds them together. The fragments, instead of flying off into space, fall back down onto the combined surface. Over hours or days, the debris settles. The two planetesimals have become one, a single larger body with an irregular shape, a lumpy profile where the two original masses are still distinguishable. This is how protoplanets form. Bodies massive enough that their own gravity begins to shape them, pulling them into increasingly spherical forms. As more and more planetesimals merge, the growing body's gravity strengthens. Where a 1-kilometer planetesimal has negligible gravity, barely enough to hold loose debris on its surface, a 100-kilometer protoplanet has substantial gravity, strong enough to pull itself into a sphere, strong enough to compact its interior, strong enough to heat itself through the gravitational energy released by the compression. Each merger adds mass and energy, the impact energy, the kinetic energy of the colliding bodies is converted into heat. Some radiates away into space, but much of it remains, warming the interior. At the same time, radioactive elements scattered throughout the rock, isotopes of uranium, thorium, potassium, are decaying, releasing heat steadily. As the protoplanet grows, as more material piles on top, the pressure at the center increases, and pressure creates heat. The interior begins to warm, to soften, to become plastic. Heating their interiors through the energy of impacts and the decay of radioactive elements, the protoplanets begin to differentiate. The densest materials, primarily iron and nickel, sink toward the center, pulled by gravity. The lighter materials, silicate rocks rich in oxygen, silicon, magnesium, and aluminum, float upward, forming a mantle around the metallic core. This process releases even more energy, gravitational energy, as the dense material falls and the light material rises. The interior grows hotter still. In the inner solar system, where temperatures are too high for ice to survive, where the sun's heat has driven away all the volatile compounds, the protoplanets are made primarily of rock and metal. They are smaller than their counterparts in the outer system, because there is simply less material available. Ice cannot condense here, so the only materials that can accrete are the refractory elements, silicon, iron, magnesium, that can withstand the heat. These inner protoplanets grow slowly, competing for the limited supply of rocky material, colliding frequently in the crowded inner disk. In the outer reaches, beyond what will one day be called the frost line, the distance from the sun where temperatures drop low enough for water ice to condense, ice is abundant. Here, there is much more material available to build planets. The outer protoplanets grow much larger, eventually becoming the gas giants. Jupiter, Saturn, Uranus, Neptune. These massive bodies grow fast enough that they can capture hydrogen and helium from the disk, gathering thick atmospheres of gas around their rocky icy cores, transforming into entirely different types of worlds. But though that is a different story, one we will not follow today, it influences what happens in the inner system. Jupiter's massive gravity stirs the disk, sending planetesimals on wild orbits, preventing a planet from forming in the region that will become the asteroid belt, its presence shaping the entire architecture of the solar system. Our focus is on one particular protoplanet, orbiting in the inner disk at just the right distance from the Sun, not too close where the heat would vaporize any water, where even rock softens and flows, not too far where the cold would freeze everything solid, where even carbon dioxide becomes ice. This is the region that will one day be called the habitable zone, the Goldilocks zone where conditions are just right, and this protoplanet, still growing, still gathering mass, is the seed of Earth. It is not alone in this region. There are other protoplanets nearby, perhaps 4 or 5 major bodies, each claiming its own section of the disk, each sweeping up the planetesimals in its vicinity. They are in a race, competing to grow fastest, to dominate their orbital zones. The winner will survive. The others will eventually collide with something, merging into larger bodies or being shattered and scattered. Picture it now, not as the blue marble you know from photographs, not as the world of oceans and continents and clouds, but as something far more alien, far more violent, far more primordial. It is perhaps half the size it will eventually become, maybe 8,000 kilometers in diameter, compared to the modern Earth's 12,000. Its mass is only a fraction of what it will be, and thus its gravity is weaker, its hold on any atmosphere tenuous. Its surface is not solid but molten, a roiling ocean of liquid rock that glows with its own light. Every impact adds energy, adds heat, and with impacts occurring constantly, dozens per day, hundreds, sometimes thousands during particularly intense bombardment periods. There is no time for the surface to cool. Any crust that tries to form is immediately broken apart by the next impact, remelted, stirred back into the magma ocean. The entire outer layer, perhaps hundreds of kilometers deep, is liquid, a sea of melted stone churned by convection currents that rise and fall like waves in a terrible sea. The temperature at the surface hovers around 1500 degrees Celsius, hot enough that the rock glows a dull red in darker regions and bright orange-white where it is hottest. Heat radiates upward, visible as a glow even from space. If you could somehow survive here, hovering above the surface, the thermal radiation would be intense enough to incinerate anything organic instantly. The surface is constantly in motion, bubbles of hot magma rising from below, spreading out, cooling slightly, then sinking again as cooler, though still molten rock descends. It is a perpetual cycle, a convection cell on a planetary scale. The sky above this molten world is not blue, not the familiar azure of Earth's modern atmosphere. There is no oxygen yet, no water vapor in any significant amount. The atmosphere that exists is thin and hot, composed mostly of gases released by the impacts themselves, carbon dioxide exhaled from vaporized rock, sulfur compounds from metallic minerals, traces of nitrogen, perhaps some helium and neon, the noble gases that don't react but simply float. The air, such as it is, shimmers with heat, distorting any view of the stars beyond. The sun, still young and somewhat dimmer than it is today, about 70% of its current brightness, hangs in that sky, but it is often obscured by the clouds of debris that fill the disk, by the dust kicked up from each new collision. When visible, it appears slightly larger than it does from modern Earth, because the young planet's orbit is slightly closer, still settling into its final configuration. But the sun's light is not the brightest thing in the sky. That honor belongs to the continuous display of meteors, the stream of planetesimals and fragments that rain down constantly, streaking through the thin atmosphere in glowing arcs before slamming into the magma ocean below. and the collisions continue, unending, relentless. Small impacts, large impacts, each one adding its own violence to the chaos. Some that merely splash the magma ocean, creating momentary craters that fill in within seconds, ripples spreading outward before being smoothed away by the liquid surface. Others that send waves of molten rock rippling across the surface. Tsunami of magma, hundreds of meters tall, traveling at hundreds of kilometers per hour, crashing against each other, creating interference patterns that make the entire surface undulate. The largest impacts from planetesimals, dozens of kilometers across, punch deep into the magma ocean, possibly reaching the more solid interior below, excavating material from depth and throwing it upward, creating temporary mountains of splashed magma that slowly collapse back down. Each impact adds mass, each adds heat, each shapes the growing world. The energy budget of the young Earth is dominated by impacts. More energy comes from collisions than from the sun. More heat is generated by the constant bombardment than by radioactive decay. The planet is being forged literally by fire, by the kinetic energy of infall transformed into thermal energy, into heat, into the glow that makes the surface shine. Slowly, over millions of years, Earth clears its orbit, its gravity pulling in most of the material nearby. The zone around its orbital path becomes emptier, swept clean as each planetesimal is either captured or deflected into a different orbit, until the impacts become less frequent, less intense. The bombardment doesn't stop entirely, but it slows. Days pass between major impacts rather than hours. The surface begins, just begins, to have moments of relative calm. But the young Earth is not yet stable. Its surface is too hot, its interior too chaotic. Great plumes of magma rise from deep below, driven by convection in the mantle beneath the magma ocean, erupting in volcanoes that dwarf anything seen in modern times, anything imaginable in the familiar world. These are not the cone-shaped mountains you picture when you think of volcanoes. They are vast fissures in whatever crust manages to form, cracks that spew magma continuously for decades or centuries, creating enormous flood basalt provinces that cover areas larger than continents. Rivers of lava stretch for hundreds, sometimes thousands of miles, flowing across the featureless landscape at speeds of tens of kilometers per hour, faster than a human could run, faster than most animals could flee. They flow until they reach a lower area where they pool, creating temporary lakes of molten rock, glowing hellscapes that cool slowly from the edges inward. Over weeks or months, a thin crust forms on top of these lava lakes, dark and solid, insulating the liquid below. But before cooling into dark, cracked stone that could almost be called land, another impact arrives, and within hours or days, another impact melts that stone again, shattering the fragile crust, mixing it back into the magma ocean, and the cycle continues, endless, exhausting. Hidden in this chaos, buried beneath the violence and the heat, invisible beneath the glowing surface and the bombardment from above, is the quiet possibility of everything to come. The fundamental architecture is forming. The iron core is growing. The mantle is organizing. The first hints of a crust are appearing, even if they don't yet survive. This ball of fire, this glowing ember of a planet, will one day be a world of oceans and forests, of mountains and rivers, of ice caps and deserts, of creatures that swim and fly and think, of beings that will look up at the stars and wonder where they came from, but not yet, not for billions of years. For now it is only chaos, only heat, only the raw, brutal, magnificent process of planetary formation. A world almost finished. After perhaps 50 million years, a mere blink in geological time, yet an eternity on human scales, longer than humans have existed, longer than mammals have existed, longer than most species of any kind have existed. Earth has grown to nearly its final size. It has swept its orbit clean of most planetesimals, capturing them one by one, absorbing their mass, adding their material to its own growing bulk. The few that remain have been perturbed into different orbits, sent spinning away into the inner or outer solar system, no longer on collision courses with Earth. The rate of impacts has slowed dramatically. Where once hundreds of planetesimals struck per day, now only a handful arrive each year. The major bombardment is over, though it will never truly end. Even today, billions of years later, meteors still fall, asteroids still occasionally strike, but at a rate so slow compared to these early days that Earth's surface can remain stable for eons between major impacts. The disk itself is thinning, much of its material either accreted into planets or blown away by the solar wind, the stream of charged particles that flows constantly outward from the Sun, pushing against anything not bound by gravity. The Sun has entered a phase called the T-Tauri stage, where young stars become highly active, generating powerful winds and intense radiation. This solar wind sweeps through the inner solar system like an invisible broom, pushing the remaining dust and gas outward, clearing the space between planets, transforming the dusty disk into the relatively empty void that characterizes the modern solar system. The young planet is just beginning to cool. The surface temperature is dropping, slowly but steadily, with fewer impacts to add heat. With no continuous bombardment to stir the magma ocean, the natural process of cooling can finally begin. Heat radiates into space, infrared photons carrying thermal energy away, and nothing replaces it. The magma ocean, which has been entirely liquid for tens of millions of years, starts to crystallize from the bottom up as the pressure at depth forces minerals to solidify even at high temperatures. Its surface, while still molten in places, while still glowing red-hot in regions where upwelling brings fresh magma to the top, has started to form a thin, unstable crust in others. This crust is not like the solid ground you walk on today, not like the stable continents and ocean floors that will eventually cover the planet. It is thin, perhaps only a few kilometers thick at most, constantly broken and reformed by volcanic activity and by the remaining impacts that still occur, though less frequently. In some places, it forms islands of dark stone floating on the magma ocean, temporary continents of solidified basalt that drift and collide and break apart. In others, it cracks and sinks, pulled back down into the molten interior, subducted beneath other plates, remelted and returned to the magma. This is the first tentative beginning of plate tectonics, the process that will shape Earth for billions of years. The crust is divided into plates, but they are not yet stable, not yet thick enough to support mountains or to resist the convection currents below. They move rapidly by modern standards, driven by the vigorous circulation in the still hot mantle, colliding and separating on timescales of thousands of years rather than millions. The interior itself is beginning to organize, to differentiate into distinct layers. The heaviest elements, primarily iron and nickel, have been sinking toward the center since the planet first began to form, pulled by gravity, working their way through the silicate mantle like drops of mercury sinking through water. This process, called differentiation, is nearly complete now. Most of the metallic material has reached the core, forming a sphere of liquid iron-nickel alloy, roughly 3,000 kilometers in radius, almost half the planet's total radius. This process releases enormous amounts of gravitational energy, the energy of material falling from the mantle to the core, a distance of thousands of kilometers. This energy is converted to heat, which adds to the heat already present from radioactive decay and from the impacts that continue, though less frequently than before. The core is not uniform. At the very center, where the pressure is greatest, the iron is beginning to solidify despite the intense heat. This inner core is tiny yet, perhaps only a few hundred kilometers across, but it is growing slowly as the planet cools, as more iron crystallizes out of the liquid outer core. The transition from liquid to solid releases latent heat, the heat that was required to melt the iron in the first place, and this heat drives convection in the outer core, creating the currents that will over time generate Earth's magnetic field. Around the core, lighter rock, silicates rich in magnesium, calcium, and aluminum, forms the mantle, a thick shell of semi-solid material that extends from the core mantle boundary to the base of the crust. The mantle is hot, unimaginably hot, with temperatures ranging from around 2000 degrees Celsius at the top to over 4000 degrees at the bottom. Yet despite these temperatures, most of it is solid, or at least solid enough to transmit seismic waves, solid enough to have structure. The immense pressure prevents it from melting, squeezing the atoms together so tightly that they cannot move freely, even at temperatures that would vaporize rock at the surface. But solid does not mean immobile. On long time scales, the mantle flows. It convects, hot material rising from near the core, cooling as it rises, eventually reaching the base of the crust where it spreads out horizontally before descending again. This convection is agonizingly slow by human standards. The rock moves at rates of centimeters per year, speeds at which you could almost watch paint dry by comparison. Yet over millions of years, this flow transports enormous amounts of heat from the interior to the surface, and it drives the motion of the plates above, pushing continents around, opening and closing ocean basins, building mountains that will, in time, flow and circulate, driving the motion of the crust above. But for now, everything is still too hot, still too chaotic for clear boundaries, for the neat organization of modern Earth. The young Earth is a gradient of density and temperature, from the blazing core where iron melts despite crushing pressure, through the thick mantle where rock flows like honey, to the slightly cooler surface where the first solid crust struggles to exist, with no sharp divisions, no clear structure, everything blending into everything else in a continuum of heat and pressure and composition. And yet, structure is coming. Gravity is patient, relentless, working without rest or fatigue. Heat dissipates slowly, but inevitably, radiating into space, carrying away the energy that keeps the interior molten, and the processes of differentiation and cooling will continue for millions of years, gradually transforming this ball of molten rock into something more organized, more stable, more capable of supporting the surface features, eventually, the life that will define it. The architecture is being built, layer by layer from the core outward, the foundation upon which everything else will rest. But before that can happen, before Earth can truly become the world it is destined to be, one final catastrophe must unfold. One last collision more violent than any before, more consequential than all the others combined, that will reshape the planet and give it a companion that will orbit it for billions of years to come. The coming of Theia, somewhere else in the inner solar system, in an orbit that occasionally brings it close to Earth's path, another protoplanet has been growing. We call it Theia, after the Greek Titaness, who was the mother of the moon in mythology. Though of course no one was there to give it a name when it actually existed, no civilization to witness its existence, no telescopes to observe its slow approach. The name is a gift from the future, given by the humans who would eventually piece together the story of what happened from the evidence left behind. Theia is smaller than Earth, perhaps the size of Mars, but it is still a substantial world in its own right, perhaps half Earth's mass, several thousand kilometers in diameter. Like Earth, it has a molten surface, though its magma ocean is not as deep, not as thoroughly churned by impacts, because its smaller gravity couldn't capture as many planetesimals. Like Earth, it has a differentiating core, iron and nickel sinking toward the center, releasing heat, warming the interior. Like Earth, it follows its own orbit around the young sun, tracing an elliptical path through the inner solar system, a path that has been stable for millions of years. Imagine Theia from a distance. It glows with its own heat, a reddish sphere hanging in space, smaller than Earth but still impressive, still planetary. Its surface shows variations in brightness, darker regions where cooler magma has formed a temporary crust, brighter regions where active volcanism brings fresh material to the surface. If you could map Theia's surface, you would see it constantly changing, the patterns of light and dark shifting over days and weeks as the convection currents in its magma ocean rearrange the surface. Its atmosphere is thin, wispy, barely noticeable. Like young Earth, it cannot hold on to gases effectively. Its gravity is too weak, its surface too hot. Any atmosphere that forms from volcanic outgassing is quickly lost to space, stripped away by the solar wind, or simply evaporating as individual molecules gain enough velocity to escape. So Theia orbits in near vacuum, its surface exposed to space, its heat radiating directly into the darkness. For millions of years, Theia follows its own path, sometimes coming closer to Earth's orbit, sometimes moving farther away, the distance between them changing as both planets pursue their elliptical journeys around the Sun. At times they are on opposite sides of their orbits, separated by hundreds of millions of kilometers, so distant that each would appear to the other as merely a bright star, a point of light indistinguishable from Venus or Mercury, except by its motion. At other times they are closer, both on the same side of the Sun, and the distance shrinks to tens of millions of kilometers, but their orbits do not cross. They are held in a complex gravitational dance with the Sun and the other growing planets, their paths carefully balanced, each keeping to its own lane. But orbits in the early solar system are not stable, not in the long term. There are too many bodies, too much gravitational interference, too much chaos left over from the formation process. Jupiter, massive and distant, tugs on everything in the inner system. Venus, if it has formed yet, pulls from one side, Mercury from another. Each impact the Earth or Theia experiences, each planetimal captured, changes the mass slightly, and thus alters the gravity slightly, and these tiny changes accumulate. Small perturbations accumulate over time. A close pass by a large planetesimal nudges the Theia's orbit slightly. The gravitational pull of Jupiter during a particular alignment changes Earth's orbit by a tiny amount. These changes are minuscule at first, mere meters of difference in position, fractions of a degree in orbital angle, but orbits are sensitive to initial conditions. Small changes compound. Over thousands of orbits, over millions of years, the paths drift. Orbits shift, slowly at first, imperceptibly, then faster as resonances develop, as the timing of gravitational tugs aligns in unfortunate ways. Computer simulations of the early solar system show that this kind of orbital instability is inevitable. With multiple planet-sized bodies orbiting relatively close together, the system cannot remain stable indefinitely. Eventually, within the first 100 million years, something has to give. Orbits must change, bodies must collide or be ejected. The early solar system is like a game of gravitational billiards, and eventually the balls must strike. And one day, though day is perhaps the wrong word for an event that unfolds over hours or days, for a moment that has been building for millions of years, Theia's orbit intersects Earth's, not just approaches closely, not just a near miss, but truly intersects, the two paths crossing in space so that both planets will arrive at the same point at the same time. The two worlds, each forged from the same nebula, each carrying within them the ashes of dead stars, elements created in supernovae that exploded billions of years before the Sun was born, are on a collision course. There is no awareness, no fear, no anticipation. Earth does not know Theia is approaching. Theia does not know it is about to die. They are not conscious, not alive, merely masses of rock and metal following the laws of physics, responding to gravity, unable to change course or to comprehend what is happening. Only gravity, pulling the two bodies together with increasing force as they approach, the mutual attraction growing stronger as the distance shrinks. Only momentum, the motion they inherited from the swirling disk, now carrying them toward destruction. Theia accelerates as it falls inward, its speed building as it drops down the gravity well toward Earth. From far away, moving at its normal orbital velocity, it swings in toward Earth's position. Earth's gravity pulls it forward, adding to its speed, bending its path. Faster and faster. Theia comes, falling toward Earth like a stone dropped from a great height, though there is no up or down in space, only the inexorable pull of gravity. While Earth, oblivious, continues its own orbit, unaware of what is about to happen. Its surface churns with its magma ocean, volcanoes erupt, the thin crust breaks and reforms, life continues, or rather the pre-life processes continue, the chemistry that will eventually lead to life, the slow organization of molecules in the seas that have not yet formed. The planet is going about its business of formation, of cooling, of growing, with no hint that in a few hours or days everything will change. The two worlds meet not head-on but at an angle, a glancing blow at unimaginable speed. The impact angle is perhaps 45 degrees, not perpendicular, not parallel, but somewhere in between. This angle is crucial. A head-on collision would have destroyed both planets completely, shattered them into fragments too small to reform. A more glancing angle would have resulted in less catastrophic damage. But this angle, this particular trajectory, will create something new. Imagine, if you can, a planet-sized object, thousands of kilometers across, moving at tens of thousands of kilometers per hour, perhaps 40,000, perhaps 50,000, speeds that make hurricanes seem like gentle breezes, speeds where the kinetic energy is so enormous that it defies intuition. Imagine it striking another planet-sized object. The energy released in that instant is beyond any comparison available to human experience, beyond anything witnessed in recorded history. It is more than all the nuclear weapons ever built, detonated simultaneously, multiplied by millions. It is more than the total energy output of the sun for days, concentrated into a single terrible moment. It is the energy of orbital motion, of gravitational potential, of the mass of worlds, all transformed in an instant into heat and violence. The great impact. The collision begins at the point of contact, at the single spot where Theia's surface first touches Earth's. For a fraction of a second, the two surfaces are pressed together, compressed by the combined momentum of both planets. The pressure at that point is indescribable, beyond anything that exists in nature, except perhaps in the cores of stars. Rock cannot withstand such pressure. Atomic bonds break, molecules disintegrate. Theia's crust, already thin and molten, vaporizes instantly, transformed from solid matter to gas to plasma in a fraction of a second. Rock becomes gas, becomes plasma, passing through all the phase changes in the blink of an eye, skipping from solid to liquid to gas in microseconds, the temperature spiking to tens of thousands of degrees. The very atoms are ionized, electrons stripped away, leaving bare nuclei and free electrons, a state of matter that only exists in the most extreme environments. The shockwave spreads outward from the impact site at supersonic speed, actually faster than sound can travel through the material, because this is not a normal pressure wave but a shock wave, a discontinuity in the medium itself. It races across both worlds at velocities measured in tens of kilometers per second, faster than meteors, faster than anything except light. As it passes through material, it compresses it, heats it, fractures it, shattering crust, liquefying stone, breaking apart the careful structure that gravity has spent millions of years creating. releasing energy that had been locked in the chemical bonds of matter since the formation of the solar system, stored in the arrangement of atoms, now suddenly freed. Earth's surface erupts in response. Where the Theia struck, the crust, what little crust exists, simply disappears vaporized. The magma ocean beneath is blasted away, the liquid rock turned to vapor. A vast plume of vaporized rock explodes upward, a jet of plasma expanding at hypersonic speeds, carrying with it fragments the size of mountains, the size of continents, pieces of both worlds torn free by the impact. These fragments are hurled into space at velocities high enough to escape Earth's gravity, shooting outward like bullets from a gun, some fast enough that they will eventually escape the solar system entirely, carrying pieces of Earth and the Theia into interstellar space. The planet itself rings like a bell, not producing sound. There is no air to carry sound, but vibrating at frequencies determined by its size and composition. Seismic waves ripple through its interior, pressure waves and shear waves, traveling through the mantle and core at different speeds, reflecting off the core mantle boundary, off the surface, interfering with each other in patterns of unimaginable complexity, creating standing waves that make the entire planet pulse and deform. For hours after the impact, Earth continues to vibrate, its shape oscillating between slightly more spherical and slightly more oblate, ringing with the energy of the collision. For a brief moment, perhaps hours, perhaps days, Earth is not a planet but a cloud, not a solid object but a diffuse mass of gas and liquid and solid all mixed together. Its outer layers have been peeled away, exposed to space, blown outward by the force of the impact. The mantle material that was buried beneath kilometers of crust is now at the surface, glowing white-hot, radiating heat into the vacuum. The temperature at the surface has spiked to over 7,000 degrees Celsius, hotter than the surface of the sun, hot enough that silicon and iron and every other element is a gas. The atmosphere, such as it was, the thin layer of carbon dioxide and nitrogen and water vapor that had begun to accumulate, is blown away entirely, lost to the vacuum in an instant. The shock wave from the impact pushes the gas outward faster than it can orbit, faster than gravity can hold it, and it expands into space, dispersing, lost forever. Earth is briefly naked to space, its surface exposed, no blanket of air to protect it or to trap heat. The surface is a roiling storm of magma and vapor, with no clear boundary between solid and gas, between planet and space, everything mixed together in a chaotic gradation from the dense core to the tenuous outer envelope of vaporized rock. Imagine looking at Earth from a distance in these moments. You would not see a sphere, you would see something more like a comet, a glowing core surrounded by a vast atmosphere of vapor, streamers of plasma extending outward, the whole system churning and evolving as gravity tries to reassert control. The Edda fares no better. In fact, the Edda fares worse. The collision has torn it apart completely, shattered it into pieces of every size. Its core, the dense iron and nickel at its center, perhaps 1,000 kilometers across, punches through Earth's mantle like a bullet through tissue. The mantle cannot stop it. The core is too dense, moving too fast, carrying too much momentum. It penetrates deep into Earth's interior, plowing through the silicate rock, melting everything in its path, creating a channel of liquefied stone behind it. Eventually, far below the surface, Theia's core merges with Earth's own core, adding mass to the growing metallic center of our planet, adding spin because Theia's core carried angular momentum, hitting at an angle that imparts rotation. The two cores swirl together like cream stirred into coffee, mixing, their iron and nickel alloying, their heat combining, the whole system reorganizing around this new larger center of mass. Adding heat from the energy of the merger, the kinetic energy converted to thermal energy, warming Earth's core by thousands of degrees, heating it enough that it will remain liquid for billions of years, long enough for life to evolve under its protective magnetic field. The rest of Theia, its mantle, its crust, everything that was not dense enough to sink immediately into Earth's interior, is shattered into countless fragments of every imaginable size. Some pieces are tiny, dust and vapor, the smallest products of the collision. Others are enormous, chunks of planetary crust hundreds of kilometers across, still glowing with the heat of impact. Some falling back to Earth, raining down over the following days and weeks, adding their mass to the growing planet, splashing into the magma ocean, creating new impacts, further churning the surface. Others escaping into space entirely, shot away so fast that even Earth's enhanced gravity, now stronger because Theia's core has been added, cannot hold them, destined to wander the solar system as asteroids, or to eventually be swept up by other planets. And some, crucially, entering orbit around Earth, moving at just the right velocity to circle the planet rather than escape or fall back. Those fragments that enter orbit do not do so neatly, do not arrange themselves in a tidy ring. They form a ring, or rather multiple rings, of debris circling Earth at various distances and inclinations, a chaotic swarm of material orbiting in every direction. Some pieces collide with each other almost immediately, fragmenting further or sticking together depending on the speed of impact, breaking apart or merging, creating still more fragments, filling the space around Earth with debris. Others spiral inward, their orbits decaying due to tidal forces and the drag of the tenuous envelope of vapor that still surrounds Earth, raining back down on the molten surface over weeks and months. Still others drift outward, their orbits slowly expanding over time as tidal interactions with Earth transfer angular momentum, pushed away by the same forces that will eventually push the Moon into its current orbit. The ring is spectacular, though of course no one is there to see it. From Earth's surface, if there were any surface to stand on, which there isn't, the ring would fill the sky, a band of glowing material stretching from horizon to horizon, brighter than the full moon, bright enough to cast shadows. Individual pieces large enough to resolve as disks, rather than points, would be visible, tumbling slowly, catching sunlight, glowing with their own heat. The ring casts a shadow on Earth's surface during the day, a moving band of darkness that sweeps across the planet as Earth rotates beneath it. But gravity, as always, works patiently, tirelessly, without hurry but without rest. The ring of debris is unstable, a temporary configuration that cannot last. Objects in different orbits move at different speeds, their paths crossing and recrossing. Collisions are inevitable, and each collision either breaks objects apart or allows them to stick together, depending on the velocity and angle. Over time, over thousands and then millions of years, the fragments begin to coalesce, to aggregate, following the same process that built the planets themselves. Larger pieces sweep up smaller ones, their gravity pulling in nearby fragments, growing steadily. Collisions become accretions, destructive impacts becoming constructive as the velocities decrease, as the largest objects begin to dominate gravitationally. The ring begins to organize itself, material concentrating into a few large clumps rather than countless small fragments. Slowly, unevenly, a new body forms in orbit around Earth, built not from the original protoplanetary disk, but from the shattered remnants of two worlds, a child born from violent destruction. The birth of the Moon, after perhaps 10 million years, a geological instant, yet long enough for mountains to rise and be eroded away many times over on a more settled world. The process is complete, or nearly so. The debris ring has consolidated into a single large body, though some smaller fragments still orbit independently, though dust and pebbles still rain down occasionally, but the major accretion is done. The Moon exists. It orbits Earth at a distance much closer than the Moon orbits today perhaps only 15,000 kilometers away, measured from center to center, compared to the 384,000 kilometers of the present day. This is close, incredibly close, less than 5% of the modern distance. At this range, the moon is not a distant object, but a looming presence, filling a substantial portion of the sky, its gravity pulling powerfully on Earth, its tidal influence overwhelming. This is the moon, though it looks nothing like the familiar silver disk you see in the night sky on a clear night. Nothing like the friendly face that has watched over humanity since the beginning. The young moon is hot, its surface still glowing from the heat of its formation, from the countless impacts that built it, from the gravitational energy released as fragments merged. The entire outer layer is molten, a magma ocean even deeper than the one that once covered Earth. Because the moon formed quickly, the energy of accretion trapped inside faster than it could radiate away. Lava oceans cover much of it, vast seas of liquid rock, feeding and fed by the ongoing rain of smaller impacts, the last stragglers from the debris ring, and by the tidal heating caused by Earth's powerful gravitational pull. Earth's gravity doesn't just hold the moon in orbit, it squeezes it, pulling on the near side more strongly than the far side, creating bulges, deforming the moon's shape, and this deformation generates heat through friction as the rock flows and flexes. The moon is being kneaded like dough, stretched and compressed twice per orbit, and this tidal heating keeps the interior warm, keeps the magma ocean liquid for longer than it would otherwise remain. Because it orbits so close, the moon is locked in synchronous rotation almost from the beginning, within the first few million years of its existence, always showing the same face to Earth, just as it does today. This happens because Earth's tidal forces act more strongly on the near side than the far side, creating a torque that slows the moon's rotation until it matches the orbital period. Once locked, the moon's rotation period equals its orbital period, so the same hemisphere perpetually faces Earth, while the other perpetually faces away. From Earth's surface, now slowly re-solidifying after the catastrophe of the impact, the magma ocean cooling, a thin crust beginning to form again. The moon dominates the sky in a way difficult to describe, impossible to convey to someone who has only seen the modern moon. It appears 14 times larger in diameter than it does in the modern era, and because apparent size goes as diameter squared, it covers about 200 times more area of the sky, covering a substantial portion of the heavens, roughly 30 times the apparent size of the modern moon, stretching across perhaps 15 degrees of sky, the width of your spread hand held at arm's length, glowing with its own light. Not yet the reflected silver of sunlight, not the cool, pale light of the modern moon, but the dull red of molten rock, the orange glow of lava, pulsing and shifting as convection currents move across its surface. The moon doesn't simply reflect light, it produces light, thermal radiation from its hot surface, bright enough to see by even when the sun has set, bright enough to read by if there were anyone to read and anything to read. The light is ruddy, casting everything in shades of red and orange, giving the night a hellish quality. The tides it raises on Earth are not measured in meters, but in hundreds of meters, perhaps half a kilometer in height. Bulges of molten rock pulled up by the moon's gravity, following the moon as it crosses the sky. These are not water tides. There is no liquid water yet, but tides in the magma ocean, waves of molten stone rising and falling twice per day as the moon orbits overhead, pulling at the still molten surface, creating bulges that circle the planet twice a day, once when the moon is overhead, once when it is on the opposite side of Earth, because the tide is caused by the difference in gravitational pull, not the pull itself, and the far side is pulled less strongly than the near side, creating a bulge there too. These tides dissipate enormous amounts of energy. As the bulges travel around Earth, friction with the interior, with the parts of the planet not directly at the surface, converts kinetic energy to heat. This heats the interior further, keeping it molten, but it also slows Earth's rotation, gradually lengthening the day, transferring angular momentum from Earth's spin to the Moon's orbit. In those early days, an Earth day is only 5 hours long, perhaps even less, perhaps only 4 hours from sunrise to sunrise. The planet spinning rapidly on its axis, a legacy of the angular momentum added by Theia's impact, the oblique collision that set Earth spinning like a top. A full rotation in 5 hours means that the surface at the equator is moving at over 2 kilometers per second, creating fierce winds in any atmosphere that eventually forms, creating powerful convection cells, making weather patterns that circle the globe in hours. But the tidal forces exerted by the massive, close Moon are already beginning to slow that spin, acting like a brake, stealing rotational energy, transferring angular momentum from Earth's rotation to the Moon's orbit. The same process that happens today, but far more intensely, because the Moon is so much closer and the tidal forces scale as the cube of distance. So a Moon at 1/20th the distance creates tidal forces 8,000 times stronger. Over billions of years, this process will continue, lengthening Earth's day to 24 hours, gradually, imperceptibly, a few microseconds per year added to the day, accumulating over eons, and pushing the Moon slowly outward to its present distance, centimeter by centimeter per year, the Moon receding as it gains the angular momentum that Earth loses, climbing out of Earth's gravity well, moving toward the distance where it orbits today. But all of that is yet to come. All those billions of years of slow evolution, of gradual change, of the Earth-Moon system settling into its mature configuration. For now, Earth and Moon are a binary system, two scarred worlds orbiting their common center of mass, though that center is well within Earth. Because Earth is so much more massive, the Moon is still large enough that both bodies orbit a point between them, not just the Moon orbiting Earth, both glowing with heat, both still in the final stages of formation, both bearing the scars of violence. The great impact has reshaped both. Earth is larger now, its mass increased by perhaps 10%. Theia's core added to its own, its spin is faster, its interior hotter by thousands of degrees, its surface completely renewed, every trace of what existed before the impact erased, melted, mixed into the new configuration. And it has gained a companion, a massive Moon, larger relative to its planet than any other moon in the solar system, except possibly Pluto's Charon, a moon massive enough to influence everything about Earth's future, a massive moon that will influence its climate through tides, through its gravitational pull that will stabilize Earth's axial tilt, preventing the wild oscillations that would otherwise make Earth uninhabitable, keeping the seasons regular and predictable over billions of years, its tides mixing the oceans that will eventually form, distributing heat and nutrients, creating the intertidal zones where some scientists believe life first emerged, its very stability, for as long as both worlds exist, a constant companion, a partner in the cosmic dance, forever linked to Earth by the violence of their birth. Look up at the Moon tonight. If the sky is clear, if the weather permits, if clouds don't obscure your view, see its craters, its Maria, the dark plains of solidified lava that fill the ancient impact basins, the seas that are not seas, named by astronomers who thought they saw oceans but found only stone, its highlands, the bright, heavily cratered regions that represent the ancient crust, battered by billions of years of impacts. The familiar pattern of light and dark that humans have seen for millennia, that has inspired countless myths and stories, that has marked time and tides for as long as anyone can remember. Know that you are looking at a piece of Earth's history, at the remnants of a collision so violent it destroyed two worlds and created two new ones, at rock that was once part of Earth or part of Theia or both, mixed together, shattered, melted and reformed. The moon is not just a satellite, not just an object in orbit, not merely the thing that pulls the tides and lights the night. It is a monument, a memorial, a permanent record written in stone of the chaos from which our world emerged, a witness to the violence of planetary formation, a reminder that even the most serene and beautiful things can be born from catastrophe. The cooling begins. After the impact, after the debris has settled, after the moon has formed and moved into its orbit, after the ring has coalesced, and the last fragments have either been captured or escaped, Earth finally, slowly, painfully, begins to cool. The process is not quick, not measured in years or decades or even centuries. Millions of years pass, stretching into tens of millions, an incomprehensible span of time during which the planet gradually releases the enormous amount of heat accumulated during its formation, and especially during the Great Impact. The surface, heated to temperatures where rock vaporizes, where silicon and oxygen exist as gas, where the very atoms are torn apart, gradually cools to temperatures where rock merely melts, still liquid but no longer plasma, then to temperatures where it can begin to solidify, where the first crystals form in the cooling magma, where the phase transition from liquid to solid finally becomes possible. This happens slowly, unevenly, with the hottest regions remaining molten while cooler areas begin to harden. The cooling happens from the top down, naturally, inevitably, because heat radiates into space from the surface. The surface is in contact with the vacuum, exposed to the cold of space, which is essentially absolute zero except where warmed by sunlight. Heat flows from hot to cold, from the molten interior to the frigid void, and the temperature gradient drives the cooling. Beneath the surface, insulated by the layers above, the interior remains hot for much longer, cooling only gradually as heat works its way upward through conduction and convection. The first crust forms in patches, islands of hardened stone floating on the magma ocean like ice floes on an Arctic sea, except these floes are stone and the sea beneath is molten rock. These patches are thin, perhaps only a few meters thick at first, unstable crust that forms wherever the surface is slightly cooler, wherever convection brings cooler material to the top, or where the magma has a composition that solidifies at a higher temperature, constantly broken apart by impacts, less frequent now than before, but still occurring regularly, and by the convection currents in the molten layer below, which push and pull at the crust, bending it, fracturing it, subducting it back into the magma, where it melts again. But they represent a threshold crossed, a fundamental change in the nature of Earth. Earth is no longer entirely liquid, no longer just a sphere of molten rock. It is beginning to develop a solid surface, beginning to have a crust distinct from the mantle, beginning to have the layered structure that will characterize it for the rest of its existence. The transition from magma ocean to solid planet is beginning, the slow transformation that will take millions of years, but has now irreversibly started. Watch one of these early, crustal patches form, in a region where the magma ocean is slightly cooler, perhaps shaded by a mountain-sized fragment, still orbiting nearby, or perhaps where the convection has brought deeper, cooler material to the surface. Crystals begin to form in the liquid rock. Tiny at first, microscopic, individual minerals crystallizing out of the melt, olivine, pyroxene, plagioclase, the building blocks of basaltic rock. These crystals float in the magma, drifting, sometimes sinking if they're dense, sometimes rising if they're light, sometimes colliding and sticking together. More crystals form as the cooling continues. The partially crystallized magma becomes slushy, a mixture of solid and liquid, like a snow cone melting in reverse. The solid fraction increases. The crystals pack together, interlocking, forming a coherent mass, and suddenly there is solid rock, a layer floating on the surface, insulated from below by the remaining magma, cooled from above by radiation to space. The crust thickens over time, cooling from the top down, the process accelerating as the surface layer insulates the magma below, slowing convection, allowing more crystallization. The uppermost layer solidifies into dark basalt, similar to the rock that forms the ocean floor today, rich in iron and magnesium, dark in color because of the iron content. Below it, the magma remains liquid, slowly convecting, rising where it is hot, sinking where it cools, continuing the circulation that transports heat from the interior to the surface. This convection helps carry heat to the surface where it can radiate into space, accelerating the cooling process, creating a positive feedback loop where cooling enables more cooling. Over millions of years, the patches of crust grow larger, thicker, more stable. They collide with each other, pushed together by the convection currents beneath, sometimes overriding each other in primitive subduction zones, sometimes welding together to form larger plates. The first continents begin to form, though they don't yet look like continents as we know them. They're small, perhaps only a few 100 kilometers across, more like large islands than true continents, made of slightly different rock than the basaltic crust because they've been processed by volcanism and partial melting. The atmosphere, blown away by the impact, erased in an instant by the violence of the collision, begins to reform slowly, molecule by molecule. Gases trapped in the interior of the planet, dissolved in the magma ocean or locked up in minerals, escape through volcanic eruptions and through the cracks in the thin crust, the fissures that open wherever plates pull apart or collide. Carbon dioxide bubbles out of the magma, released as the pressure decreases, along with water vapor, nitrogen, and smaller amounts of other gases, sulfur dioxide from the breakdown of sulfide minerals, carbon monoxide from the incomplete oxidation of carbon, hydrogen from the breakdown of water at high temperatures. These gases accumulate above the surface, held by gravity, creating a new atmosphere, building up slowly as more and more gas is released from the interior. This new atmosphere is not like the air you breathe today, not oxygen-rich and transparent and breathable. It is thick and hot and utterly hostile to any life that might ever evolve, more like the atmosphere of Venus than modern Earth. The pressure builds as more gas accumulates, eventually reaching many times the pressure of today's atmosphere, creating a heavy blanket of gas pressing down on the surface. This new atmosphere is not transparent, not clear and blue like the modern sky. It is filled with clouds, but not clouds of water. The temperature is still far too high for water to condense into droplets. These are clouds of sulfur compounds, complex molecules formed by chemical reactions in the hot atmosphere, and clouds of vaporized rock, tiny particles of silicate that remain suspended in the air, too small to settle out, scattering the light and creating a perpetual haze. The sunlight that reaches the surface is dim, filtered through layer upon layer of haze, a dull reddish-orange glow rather than the bright white light of day. The temperature is still far too high for liquid water to exist, even if there were any significant amount of water present, which at this point there is very little. Water requires not just low temperature, but also the right pressure, and while the pressure is now sufficient, the temperature remains too high. Any water vapor in the atmosphere simply remains as gas, unable to condense, contributing to the greenhouse effect by trapping infrared radiation, keeping the surface hot. Most of Earth's water is still locked up in minerals in the interior, chemically bound to rocks trapped in crystal structures, or has been lost to space during the Great Impact, blown away when the atmosphere was stripped, or photodissociated by ultraviolet light, and the hydrogen lost while the heavier oxygen reacted with rocks. The planet at this stage is inhospitable, deadly, alien. The surface temperature hovers around several hundred degrees Celsius, hot enough to melt lead, hot enough to boil any water that might exist. The atmosphere is thick with carbon dioxide and sulfur compounds, toxic and corrosive. The surface is covered with fresh basalt, dark and barren, broken by cracks where lava still occasionally erupts. The moon hangs huge in the sky, its tidal pull creating enormous bulges in the still plastic crust. It is not a world where life could exist, not yet, not for millions of years yet to come, but it is a world preparing, slowly, for that possibility. The first atmosphere. Above the seas that do not yet exist, above the surface that is slowly solidifying, the atmosphere is changing, evolving, organizing itself into something more complex than the initial cloud of gas. It is still not the air you breathe today, still not the nitrogen-oxygen mixture that fills your lungs with every breath, that makes the sky blue and carries the scent of rain. It is heavy with carbon dioxide, perhaps 90% of the total, making it similar to the atmosphere of modern Venus, creating a powerful greenhouse effect, with methane, released from volcanic activity, from the breakdown of organic molecules delivered by asteroids, with ammonia, though this is unstable in the presence of ultraviolet light and quickly breaks down, with nitrogen, accumulating slowly as ammonia decomposes, becoming more abundant over time, eventually forming the bulk of the atmosphere as carbon dioxide is removed by other processes. It is thick, almost suffocating if you could somehow breathe it, which you couldn't, not only because of the composition, but because of the temperature and pressure. The pressure at the surface is enormous, perhaps 10 times what it is today, perhaps more. The weight of all that gas pressing down, compressing the lower layers, creating a density gradient where the air near the surface is thick as soup, while the upper atmosphere remains thinner. Sunlight filters through as a dim glow, the photons scattered by the thick haze, bouncing between particles, taking a tortuous path from the top of the atmosphere to the surface. The sun itself is rarely visible as a distinct disk, more often just a bright region in the murky sky, its light diffused and reddened. The winds are violent, restless, never ceasing, storms rolling endlessly across the surface, driven by the rapid rotation of the planet, by the temperature differences between day and night, by the convection in the thick atmosphere. Great cyclonic systems form and dissipate, bands of clouds circling the planet at different latitudes, jet streams of gas rushing from west to east at hundreds of kilometers per hour, lightning flashes constantly, enormous bolts arcing between clouds, or from clouds to the surface carrying millions of volts, bright enough to briefly illuminate the landscape below with harsh white light. But inside this sky, hidden in the chaos and the chemistry and the endless circulation of gas, the stage is being set for everything to come. This atmosphere, hostile as it is, deadly as it is also a laboratory, a chemical reactor on a planetary scale, where molecules are being built and broken apart and rebuilt in endless cycles, where the raw materials for life are being assembled atom by atom, reaction by reaction. Breathe slowly, or imagine breathing, since you cannot actually breathe here, and imagine the air pressing against your skin, heavy and warm, not fresh, not gentle, not life-giving, but heavy, pressing close to the surface of the seas that are beginning to form in the lowest regions. For millions of years it shifts and changes, its composition evolving. Volcanoes pour new gases into it, adding carbon dioxide and sulfur compounds, and water vapor with each eruption, changing the mix, altering the chemistry. Asteroids deliver icy fragments that vaporize as they pass through the atmosphere or impact the surface, adding both water and complex organic molecules of carbon, molecules that formed in the cold of interstellar space and now find themselves in this hot reactive environment. Slowly, imperceptibly, the balance tips towards something more hospitable, more conducive to the chemistry of life. The magnetic shield, born from Earth's spinning iron heart, from the convection in the liquid outer core that generates electric currents that create magnetic fields, protects this atmosphere from the fierce breath of the young sun. The sun in these early days is active, turbulent, its surface roiling with enormous flares and prominences, its stellar wind blowing much more strongly than it does today. Charged particles, protons, electrons, heavier ions, stream outward at high velocities, and when they encounter a planet, they can strip away its atmosphere over time, eroding it into space, leaving the surface exposed. Without the magnetic field, without that invisible shield, the air might have been stripped away into space, molecule by molecule, ion by ion, over millions of years, leaving Earth as barren as Mars, which lost its magnetic field early and then lost most of its atmosphere. But the shield holds firm, invisible and strong, extending thousands of kilometers above the surface, wrapping the planet like a guardian angel, like a force field in science fiction but real, physical, measurable. The charged particles of the solar wind encounter the magnetosphere and are deflected, diverted around Earth, flowing past like water around a stone in a stream, leaving the atmosphere intact, protected, preserved. The magnetic field itself is generated by the geodynamo, the self-sustaining process in the core where motion creates magnetic fields which influence motion which sustain the fields. As the liquid iron in the outer core convects, rising where it's hot, sinking where it's cool, these moving charges create electric currents, and electric currents create magnetic fields. The Earth's rotation adds a twist, the Coriolis effect organizing the convection into columns aligned with the rotation axis, creating a dipole field, a magnetic field with north and south poles, similar to a bar magnet, but vastly larger and more complex. This field has existed since shortly after Earth's core formed, since the iron separated from the silicates and sank to the center, and it will continue as long as the core remains liquid and convecting. It is one of Earth's most fundamental features, as important as the atmosphere or the oceans or the solid surface, essential for life though invisible, unnoticed except through its effects, the aurora, the behavior of compass needles, the protection of the atmosphere. A world preparing for life. Picture the scene now, millions of years after the Great Impact, the surface transformed, but still far from modern. The crust has hardened into continents, still small compared to what will come, still shifting rapidly as the vigorous convection in the mantle pushes them around. They are not yet the familiar shapes, not Africa or Asia, not America or Antarctica, but nameless landmasses, protocontinents, small islands of granitoid rock that float on the denser basaltic crust below, buoyed up by their lower density, rising above the surrounding plains like icebergs floating on water. These early continents are barren, lifeless, covered in dark volcanic rock. No plants soften their surfaces, no soil covers the bedrock, just naked stone exposed to the atmosphere and the weather. They are being weathered slowly, eroded by the harsh atmosphere, by the acidic rain that falls when sulfur dioxide combines with water vapor to form sulfuric acid, by the temperature cycles as day turns to night, by the endless wind. The weathered material, clay minerals, dissolved ions, washes into the lowlands, into the basins that are beginning to fill with water. Oceans stretch between the continents, deep and dark, covering most of the surface. These are not yet the blue oceans of modern Earth, not crystal clear and full of life, but murky, turbid, filled with dissolved minerals, colored by the iron and other elements dissolved from the rocks. In some regions, the water is greenish from dissolved iron. In others, it's reddish-brown from sediments. The temperature varies, hot in the shallows where sunlight penetrates, cooler in the depths where no light reaches, but nowhere truly cold because the whole planet is still warm from its formation. The ocean floor is young, fresh basalt, newly erupted from spreading centers where plates pull apart. Black smokers, hydrothermal vents, punctuate the seafloor at these spreading centers, chimneys of mineral deposits, where superheated water, heated by contact with magma below, erupts from cracks in the crust. The water emerging from these vents is laden with dissolved minerals, iron, sulfur, copper, zinc, and when it meets the cold ocean water, these minerals precipitate out, building the chimneys, creating a rich chemical environment, possibly the environment where life will first emerge. Above the oceans, above the continents, the atmosphere boils with storms, lightning cracking across the sky, illuminating the scene in stroboscopic flashes, striking the seas with electric fire, each bolt carrying enormous energy, momentarily creating temperatures of tens of thousands of degrees in the channel of ionized air, creating shock waves that boom across the water. These lightning strikes are not just spectacular, they are creative, constructive, driving chemistry. Every bolt stirs the chemistry of water and gas, creates new molecules through the energy it provides. Nitrogen and carbon dioxide and water vapor, inert by themselves or reacting only slowly, are forced to react in the intense heat and pressure of the lightning channel, creating new compounds, complex organic molecules, the building blocks of life, amino acids, the molecules that will form proteins, glycine and alanine and serine, simple at first but capable of linking into longer chains, nucleotides, the molecules that will form RNA and DNA, adenine and guanine, cytosine and thymine, the letters of the genetic code, scattered randomly for now, but waiting to be organized. The quiet alphabet of life itself, being written in the atmosphere and delivered to the oceans with every rainstorm. These molecules drift in the water, scattered, dilute, dissolved in the vast ocean, waiting, accumulating slowly over millions of years as more rain falls, as more lightning strikes, as more material is delivered by meteorites and comets that continue to impact the surface occasionally. The concentration is low, perhaps parts per million, perhaps less, but the volume is enormous. The ocean contains quintillions of liters of water, and even a low concentration means vast numbers of molecules, enough to experiment, enough to find combinations that work. The Earth, without knowing, without intention, without consciousness or design, is writing the first letters of the story of biology, assembling the materials that will eventually organize themselves into something that can be called alive. It is a slow process, agonizingly slow by human standards but rapid in geological time. The ingredients are gathering, the stage is being set, the conditions are slowly becoming right. But for now, it is only preparation, only the accumulation of raw materials, the establishment of conditions. The world is not yet alive, not yet green with photosynthesis, not yet filled with the sounds of living things moving and eating and reproducing. It is waiting, patient, restless beneath its storms, the chemistry happening slowly in the depths, invisible, unnoticed, but happening. The air is heavy, the oceans endless, the crust still warm from within, releasing heat through volcanoes and hot springs, creating temperature gradients that drive circulation, that mix the water, that bring nutrients from the depths to the shallows. Yet everything needed for life is now here, or will be soon. Water, the universal solvent, the medium in which chemistry can happen, now covering most of the surface in quantities sufficient to dissolve and transport and organize molecules. Energy, from sunlight, from lightning, from the heat of hydrothermal vents, from the chemical energy stored in reduced minerals, enough to drive reactions, to build complex molecules from simple ones. Raw materials, carbon, nitrogen, oxygen, phosphorus, sulfur, all the elements that life will need, available in abundance, dissolved in the water, or present in the rocks or floating in the atmosphere. And time, deep time, millions and then billions of years, enough time for unlikely things to happen, for accidents to occur, for random combinations to be tried and tried again until one works. And so, Earth breathes, If breathing means the circulation of gases through the atmosphere, the exchange of carbon dioxide and oxygen through chemical reactions, the slow cycling of volatiles from the interior to the surface and back, clouds swirl in complex patterns, organized by the Coriolis effect into bands and whirls, hurricanes and cyclones spinning in opposite directions in the two hemispheres. Rain falls in torrential downpours, warm rain from the water-rich atmosphere, washing minerals from the continents, creating rivers that carve the first valleys, that transport sediment to the oceans. Waves crash against black shores, basaltic beaches and rocky headlands, eroding them slowly, breaking stone into sand, creating the first sediments. The planet is no longer only a sphere of stone, no longer just rock and metal organized by gravity. It is now a world of sea and sky, of land and water, of circulation and chemistry, of dynamic processes that interact and influence each other. The geosphere, the solid earth, affects the hydrosphere, the oceans, which affects the atmosphere, the air, which affects the geosphere through weathering and erosion, creating feedbacks, creating a system, something more than just a collection of parts. The restless interior. Let your breath slow, let your awareness sink, let your eyelids grow heavy. We are drifting deeper now into Earth's story, past the surface chaos, beyond the forming oceans and the violent atmosphere, down into the hidden realm that drives everything above. The oceans have arrived, condensed from the steam that filled the early atmosphere, delivered by countless comets, accumulated over millions of years. The atmosphere is taking shape, outgassed from the interior, modified by chemistry, protected by the magnetic field. But inside the planet, far beneath the waves, far below even the deepest roots of the continents, something powerful and restless is unfolding. To understand Earth, to truly know this world, you must look within, must descend into the interior where the heart beats and the engine runs. The surface may seem calm now, relatively speaking, but below the heart of the world is alive, churning, convecting, generating the forces that will shape continents and move mountains. Close your eyes and imagine you are sinking gently, slowly down through the crust like a ghost passing through walls. First, through solid rock, hard and cold at the surface, where rainwater seeps through cracks, where temperature is determined by the sun and the seasons, where life will eventually flourish in every crack and crevice. But as you descend, the rock grows warmer, heated from below by the geothermal gradient, the steady increase of temperature with depth that characterizes all planets. The temperature rises perhaps 30 degrees Celsius per kilometer, so that by the time you're a few kilometers down, it's as hot as boiling water, and deeper still, hotter than any oven. Then deeper, where the stone grows hotter, softer, beginning to lose its rigid brittleness, becoming more plastic, more able to flow over long time scales. The pressure is increasing too, the weight of all the rock above pressing down, squeezing everything, changing the properties of minerals, forcing atoms closer together. Under these conditions, rock behaves differently than it does at the surface. It can flow, slowly, imperceptibly, creeping along at rates of millimeters per year, but flowing nonetheless, solid yet mobile, rigid yet fluid, almost alive with motion if you watch on the right time scale. You are entering the mantle, descending through the crust-mantle boundary called the moho, entering a realm of rock that moves not quickly, not in human time, but slowly, with the patience of millions of years. The mantle comprises the bulk of Earth's volume, most of its mass, the thick shell of silicate rock that extends from the base of the crust at perhaps 30 or 40 kilometers depth, down to the core mantle boundary at 2,900 kilometers. It is not a simple uniform layer, but a complex system organized into regions with different properties, different compositions, different behaviors. The upper mantle, where you are now, is relatively cool by mantle standards, perhaps 1,300 degrees Celsius, and relatively rigid, but not rigid like steel or stone at the surface. Rigid like glass, which is technically a very viscous liquid, flowing imperceptibly, able to deform over long time scales. This upper mantle, combined with the crust above, forms the lithosphere, the rigid outer shell of Earth that is broken into tectonic plates. It's these plates that move around, colliding and separating, driven by forces from below. Deeper in the mantle, the temperature and pressure continue to increase. The rock remains solid, but becomes more plastic, more able to flow. It flows like putty, like tar on a hot day, like honey, not a liquid, not freely mobile, but viscous, resistant to flow, yet flowing nonetheless, when pushed by pressure differences or temperature differences. Not a solid, not in the rigid sense, but something in between, something that responds to stress by flowing rather than breaking, that can maintain its shape for years or centuries, but changes shape over millennia. In this mantle, heat from the core rises upward, carried by convection, stirring the stone into slow, majestic circulation that takes millions of years to complete a cycle. Hot rock deep in the mantle, heated by contact with the core, becomes slightly less dense than the rock around it. Not much less dense, perhaps only 1%, but enough. This hot rock drifts upward, moving through the surrounding mantle, rising slowly, taking millions of years to ascend thousands of kilometers, pushed by buoyancy, pulled by gravity, following the endless cycle of convection. As it rises, it cools by expansion, by adiabatic cooling, the temperature dropping as the pressure decreases. By the time it reaches the base of the lithosphere, it has cooled significantly, but is still hotter than the rock around it. It spreads out horizontally, flowing beneath the rigid plates, transferring heat to the lithosphere above, driving the motion of the plates. Then, having given up its heat, having cooled, it becomes denser and begins to sink again, descending back into the depths, completing the convection cell. This slow movement, this creeping flow, will one day push continents across the globe like rafts on a very slow river. It will open oceans where none existed, forcing continents apart, creating new oceanic crust in the gap. Atlantic-style rifting that can split a landmass in two and separate the pieces by thousands of kilometers over hundreds of millions of years. It will close oceans that once were wide, pushing continents together, crumpling the edges into mountain ranges, Himalayan-scale collision that raises peaks kilometers into the sky. It will raise mountains higher than clouds, fold and fault the crust, create the dramatic topography that makes Earth interesting, that creates climatic diversity, that influences evolution, then grind them down again over tens of millions of years through erosion, reduce them to sediment, carry that sediment to the seas, and eventually recycle it back into the mantle at subduction zones. But for now, in the young Earth, in these early days when the mantle is hotter and convection is more vigorous, it is only beginning, this grand cycle of tectonics. The plates of the crust are thin and fragile, broken into pieces more numerous and smaller than the plates of modern Earth. They float on the mantle like rafts on a deep sea of stone, like icebergs on an ocean except inverted, the lighter material floating on the denser material below, buoyed by isostasy, the principle that less dense material floats higher and more dense material sinks lower until equilibrium is reached. The boundaries between plates are active zones, places where the action happens, where the surface expression of mantle convection becomes visible. At divergent boundaries, where plates pull apart, magma rises from below to fill the gap, creating new crust, building the ocean floor, adding material to the plates. At convergent boundaries where plates collide, one is forced beneath the other, subducted back into the mantle, descending into the hot interior where it melts and is recycled. At transform boundaries, plates slide past each other horizontally, neither creating nor destroying crust, but releasing enormous energy in earthquakes, as the friction is overcome. The molten core sink deeper still, leaving the mantle behind, passing through the transition zone where the pressure becomes so great that minerals change their crystal structure, becoming denser forms of the same composition, olivine transforming to wadsleyite to ringwoodite. Each phase transition marked by an increase in density, a change in seismic velocity. Beyond the mantle, past the transition zone, you reach the outer core at a depth of 2,900 kilometers, nearly halfway to the center. Here, the world changes fundamentally. The outer core is not rock, not silicate, but metal, and not solid metal but liquid, molten despite the immense pressure, because the temperature is so high. Here, the world is liquid metal, mostly iron and nickel, with perhaps 5 or 10% lighter elements mixed in, sulfur, oxygen, silicon, elements that lower the melting point, that make the iron liquid at these temperatures and pressures. It is unimaginably hot, hotter than the surface of the sun, temperatures around 4,000 to 5,000 degrees Celsius, yet hidden beneath thousands of kilometers of rock, invisible, undetectable, except through seismic waves and magnetic measurements, and the inference of physics. This outer core is enormous, perhaps 2,200 kilometers thick, containing about 30% of Earth's mass, a vast ocean of liquid metal churning constantly, never still, never frozen. The liquid metal is always moving, flowing in complex patterns driven by multiple forces. Rivers of molten iron flow in great currents, thousands of kilometers long, hundreds of kilometers wide, moving at speeds of perhaps a few kilometers per year, slow by surface standards, but remarkably fast for something buried so deep, something under such enormous pressure, spiraling around the solid center, organized by the Coriolis effect from Earth's rotation, creating cyclonic patterns, vortices of flowing metal that persist for decades or centuries before dissipating and reforming elsewhere. These currents are driven by convection, just like in the mantle but faster, more vigorous because liquid flows more easily than solid, even very viscous solid. Heat from the inner core, from the solidification process, from radioactive decay, warms the metal, makes it less dense, causes it to rise. Cool metal, from near the core mantle boundary sinks, pulled by its greater density, creating circulation. The Coriolis effect, from Earth's rotation, adds a twist, organizing the flow into columns aligned with the rotation axis, creating the complex three-dimensional flow patterns that seismologists can now map by studying how seismic waves travel through the core. At the very heart of this metallic ocean lies the inner core, the solid center of Earth, a sphere of pure iron-nickel alloy crystallized from the liquid around it. It is tiny compared to the whole planet, only about 1,200 kilometers in radius, about the size of the Moon, but it is Earth's anchor, the seed around which everything else has gathered, the final repository of the heaviest elements. It is solid, not because it's cooler, it's actually slightly hotter than the outer core, but because the pressure is so immense, over 3 million times atmospheric pressure, that the iron is squeezed into a solid crystalline form despite the temperature. The inner core is dense, unimaginably dense, about 13 times denser than water, denser than any material you've ever handled, the atoms packed together as tightly as they can be without fusing. It is growing slowly as the planet cools, as more iron crystallizes out of the liquid outer core and adds to the solid center. Century by century, millennium by millennium, the inner core gets larger, freezing perhaps a few millimeters per year, an imperceptible growth rate, but relentless, continuing for as long as Earth exists. This growth releases latent heat, the energy that was required to keep the iron liquid, and this heat drives convection in the outer core, powers the geodynamo, maintains the magnetic field that protects the surface. Together, The inner and outer core form Earth's beating heart, the engine that powers the magnetic field, the generator that creates the protective shield. Their restless motion creates something invisible yet essential: the magnetic field, the magnetosphere, the vast region of space around Earth dominated by Earth's magnetic influence. Imagine it as an unseen shield, a force field wrapping the planet in protective arms, extending tens of thousands of kilometers into space, deflecting the solar wind, trapping charged particles in radiation belts, creating the conditions that allow the atmosphere to survive and life to flourish. Without it, without this magnetic field generated by the churning metal in the core, the charged particles of the solar wind would strip away the atmosphere over hundreds of millions of years, would burn the oceans into nothingness, erode Earth's surface, leave it barren and dead like Mars, which lost its magnetic field early in its history when its core froze and then lost its atmosphere to the solar wind. But with it, with the geodynamo operating, creating a dipole field that extends far beyond the surface, the Earth is safe, shielded, its sky held close, its seas preserved, its potential for life protected. Even now, billions of years after the formation of the core, billions of years into the future when humans will evolve and build civilizations and study the universe, you see this shield in the shimmering curtains of the aurora, the northern and southern lights, where the solar wind brushes against the magnetosphere at high latitudes, where the magnetic field lines dive down into the atmosphere near the poles. Charged particles spiral along those field lines and collide with atmospheric gases, exciting them, causing them to glow in beautiful displays of green and red and purple. The aurora is the visible manifestation of the magnetic field, the shield made luminous, a reminder that Earth is protected by forces generated thousands of kilometers below the surface. A restless crust. Return slowly upward, rising again through the liquid metal of the outer core, through the solid iron of the inner core. If you went that deep, back through the hot, flowing rock of the mantle, ascending thousands of kilometers, returning to the crust, to the thin skin of solid rock that covers the surface. Here, at the interface between the solid Earth and the ocean and atmosphere, the story of Earth continues, written in stone, recorded in layers, visible to those who know how to read it. The crust is restless, never still, always moving. It is not a single shell, not a continuous layer wrapped around the planet, but a puzzle of plates, perhaps dozens of them, each moving independently, driven by the convection in the mantle below, sliding over the plastic asthenosphere like sheets of ice on a frozen lake that's melting from below. They drift upon the mantle's slow convection, carried along by the viscous drag of the flowing rock beneath, colliding with each other, breaking apart, sliding past one another, never at rest, never in equilibrium for long. Each movement reshapes the surface, changes the map, alters the distribution of land and sea. Volcanoes rise where plates pull apart, rifts opening in the crust, magma welling up from the mantle below to fill the gap, spilling out onto the surface or onto the seafloor, creating new crust, adding to the plates. Enormous shield volcanoes, broad and low, built by countless eruptions over millions of years, layer upon layer of basalt. Explosive stratovolcanoes at subduction zones, where water-rich magma creates violent eruptions. Fissure eruptions that create vast flood basalt provinces, covering areas the size of countries with lava hundreds of meters thick. Mountains climb skyward where plates collide, the crust crumpling like paper, buckling and folding, thrust faults lifting slabs of rock kilometers into the air, folding stone into peaks that touch the clouds, creating ranges hundreds or thousands of kilometers long, barriers to weather patterns, creators of rain shadows, high-altitude deserts. The collision is slow, perhaps a few centimeters per year, but relentless, and over millions of years, the accumulated compression raises mountains, from what was once seafloor, lifts marine fossils to heights where snow never melts, creates topography that rivals anything in the solar system. Earthquakes ripple, where plates grind side by side at transform boundaries, sudden bursts of energy shaking the crust as decades or centuries of accumulated stress are released in seconds. Sudden bursts of energy that shake the crust, that can level cities if humans are there to build them, that create tsunamis if they occur beneath the ocean, that remind everyone that Earth is not a finished, stable world, but a dynamic, evolving planet where the surface is constantly being reworked. The energy of earthquakes is the energy of plate motion, stored as elastic strain in the rocks, released catastrophically when the strength of the rock is exceeded, and it breaks along a fault. All of this began in those early days after the magma ocean solidified, after the first crust formed and broke into pieces, and it has never stopped. The crust is thin, fragile, always shifting, like skin over a living body, responsive to the movements of the interior, organized by those movements, shaped by them. It is perhaps 30 kilometers thick under the continents, thicker where mountains rise, thinner where valleys sink. Under the oceans, it is much thinner, only 5 or 10 kilometers, fresher, younger, constantly being created at mid-ocean ridges and destroyed at subduction zones, recycled on timescales of hundreds of millions of years. Imagine the Earth not as a quiet rock, not as a still, unchanging sphere hanging in space, but as a breathing, moving, restless world, alive with geological processes if not biological ones. Its face changes, slowly but without pause, continuously but imperceptibly, the map redrawn over and over again across deep time. Continents drift, breaking apart and recombining in different configurations, creating supercontinents that last for hundreds of millions of years before breaking up again. Oceans open and close, the Atlantic widening as the Pacific shrinks, the Mediterranean that will one day appear and then close and then reappear as Africa and Europe approach and separate and approach again. In the vast scale of time, nothing on the surface is permanent, nothing lasts forever, everything flows, everything changes, mountains rise and are eroded away, oceans flood continents and then retreat. Deserts become rainforests, become deserts again, as continents drift through different climate zones. The surface is a palimpsest, a manuscript that has been written and erased, and written again countless times, each era leaving its traces, its fossils, its rock layers, its evidence of what came before, and beneath it all, driving it all, the restless interior continues to churn, to convect, to move, powering the surface changes, maintaining the magnetic field, keeping Earth alive in the geological sense long after similar-sized planets like Mars have gone cold and dead. This is Earth in its infancy, its adolescence, still settling, still organizing, still violent and chaotic, but already showing the patterns that will persist for billions of years. The stage is set, the pieces are in place, the conditions are established. Water, check. Atmosphere, check. Energy sources, check. Chemical ingredients, check. Protection from space radiation, check. All the prerequisites for life are now present, or soon will be. And in the depths of the oceans, near hydrothermal vents, or in tidal pools, or in some other environment we can only guess at, chemistry is becoming biochemistry, molecules are organizing, information is being encoded, and something is about to happen that will transform Earth from a merely geological world into a biological one, from a planet of rock and water into a living world. But that story, the story of life's emergence, of the first replicator, of the transition from chemistry to biology, is still ahead, still waiting to unfold, still hidden in the future of this young world. For now, let the image rest. A planet with solid crust and deep oceans, with a thick atmosphere and a protective magnetic field, with tectonic plates moving and volcanoes erupting, with storms and lightning and rain, with everything needed for life, but not yet alive, poised on the edge of the greatest transformation in its history. The shaping of continents. In the young Earth, the first continents were small, unstable fragments of crust. They floated on the oceans, battered by storms, shaken by constant eruptions. Over millions of years they grew larger, merging into bigger land masses. The crust thickened, stabilizing in places, while in others it broke apart again. This dance of land and sea would continue endlessly, creating supercontinents that one day would break apart, only to drift together again in cycles that span hundreds of millions of years. Picture one of these early continents. The rocks are dark, volcanic, raw. No soil softens their surface, no forests shade their valleys, no grass ripples in the wind. Only bare stone, cut by rivers of rain, touched by lightning. The air is still heavy with gases, but above, faint sunlight filters through. Slowly, steadily the land cools, hardens, prepares for what will come. Protection from the sun. While the crust shifts and the continents form, the core continues its restless spin, and the magnetic shield continues to hold. The young sun is fierce, blasting radiation and solar wind into space. Without protection, Earth would be scoured clean. Its atmosphere would vanish, its oceans would boil away, but the shield bends the solar wind aside, turning danger into beauty. The auroras in those early skies must have been dazzling, rivers of light dancing endlessly across the heavens. Imagine standing on a bare volcanic plain, watching curtains of green and red shimmer overhead. The air may have been harsh, but the sky was alive with light. This shield is one of Earth's greatest gifts. It is invisible, yet it has kept the planet alive for billions of years. Without it, there would be no air, no water, no life. It is a silent guardian, born from the motion of iron at the core, sustained by the planet's restless heat. A world becoming stable. Now, Earth is no longer only a sphere of molten rock. It is a layered world, each layer with its role. The solid inner core, the liquid outer core, the flowing mantle, the drifting crust, the oceans above, the air around it all. Each part works with the others, a system of balance, of energy, of constant change. And slowly the surface becomes calmer. Volcanoes still erupt, storms still rage, impacts from space still scar the land, but stability is growing. The oceans deepen. The continents spread, the atmosphere thickens into a more protective blanket. Earth is settling, finding its rhythm. Yet beneath the calm, the planet remains alive. Even today, it never stops moving. Beneath your feet, the mantle flows, the crust shifts, the core spins, the shield hums. The Earth is not just a rock, it is a living engine, a restless world that has been turning for billions of years. And in that restless turning, the stage is now set for the next chapter, the beginning of life. The first sparks of life. The Earth rests now, oceans deep, atmosphere heavy, crust shifting slowly. The fireball has become a blue and black world, water stretching like a mirror beneath a restless sky. But the story is not finished. The planet is preparing to take a step so strange, so delicate, that even now we barely understand how it happened. Earth is preparing to create life. Close your eyes and imagine those early oceans. They are not the seas you know. They are darker, thicker, filled with minerals drawn out from the crust, bubbling from the cracks of underwater vents. Lightning flashes across the skies, striking the surface, splitting molecules, sparking reactions. Sunlight, filtered through clouds of methane and carbon dioxide, reaches the water in pale beams. Within this restless sea, molecules swirl, collide, and combine. These oceans are the laboratory of creation, not guided by hands, not driven by plans, but shaped by the simple laws of chemistry, repeating themselves over and over until complexity builds. Water, carbon, nitrogen, hydrogen, stirred by energy, shaken by storms, warmed by volcanic heat. Each reaction leaves behind new compounds, new possibilities. The primordial soup. Scientists call this mixture the primordial soup. It is not food, not broth, but a churning ocean of potential. Inside it, tiny molecules assemble. First simple chains, then longer, then more intricate. Amino acids form, the letters of life's alphabet. Sugars and lipids appear, fragile but persistent. And somewhere within this soup, something extraordinary takes shape. Picture a bubble, no bigger than a grain of dust, floating in that ocean. It is made of lipids, oily molecules that cling together, forming a thin skin. Inside the bubble, water and molecules are trapped. The bubble protects them, keeps them close, lets them interact in safety. This is the beginning of a cell's body. It is not alive yet, but it is closer than anything before. Now imagine strands forming inside these bubbles, chains of nucleotides, precursors to RNA, to DNA. They copy themselves, imperfectly, with tiny mistakes. Those mistakes bring variation. Some strands survive longer, some fade away, and slowly, through this endless cycle of chance and chemistry, the first self-replicating molecules appear. This is the quiet birth of heredity, the ability to pass information from one generation to the next. It is not yet life, but it is the seed of life, the energy of the deep. Not all of this magic happens at the surface. Deep under the oceans, cracks split the crust, releasing hot water and minerals from the mantle. These hydrothermal vents, black smokers, pour heat and chemicals into the sea. Around them, strange reactions occur. Iron, sulfur, and carbon combine in unique ways. Minerals form tiny pores, chambers where molecules gather and interact. Imagine being there, floating through the dark water. No sunlight reaches these depths, but the vents glow faintly, shimmering like ghostly chimneys. Around them, chemistry thrives, molecules organize, bubbles form and burst. Energy flows here without pause. These deep vents may have been the cradles where the first living systems emerged, safe from the storms above, nourished by the Earth's heat below. The first cells. After millions of years of trial and error, the impossible happens. A bubble, filled with molecules, begins to act differently. Its strands of RNA are not just floating anymore, they copy themselves. They catalyze reactions. They hold on to energy. They change. They adapt. This is the first cell, primitive, fragile, barely alive by our standards, yet alive all the same. It grows, it divides, it drifts into the ocean currents. It has no brain, no eyes, no shape beyond a membrane and strands of chemistry. Yet it carries the spark that will one day lead to everything you know, plants, animals, humans, every life form that has ever breathed. For millions of years, these first cells remain simple. They live in the oceans, clinging to rocks, floating with the tides, dividing, evolving, changing. They eat simple molecules, release waste, take in energy from chemicals, sometimes even from sunlight. Slowly, they grow more complex. They develop new tricks. Some learn to capture sunlight directly, inventing photosynthesis. The great oxygenation. Imagine the air before this time. It is thick with carbon dioxide, methane, ammonia. There is no oxygen to breathe. But as photosynthetic cells begin to thrive, they release oxygen as waste. At first, the oxygen is swallowed by the oceans, reacting with iron, turning the seas rusty red, staining the rocks. Billions of years of oxygen bind to minerals, creating bands of iron you can still find today, stripes of stone that hold the memory of those ancient days. Eventually, the rocks are saturated. The oceans are saturated. Oxygen has nowhere else to go but upward, into the sky. Slowly, steadily, it fills the atmosphere. This is the great oxygenation event. The sky transforms. The air becomes breathable for future creatures. At the same time, the new oxygen poisons many of the old life forms, driving some to extinction, forcing others to adapt. But life is resilient. It changes, survives, evolves. The oxygen also brings another gift. High above in the upper atmosphere, it gathers into ozone, a shield that blocks harmful ultraviolet rays from the sun. For the first time, the surface of Earth becomes safer for life to crawl out of the oceans. Without this shield, life would have remained forever hidden underwater. With it, the stage is set for everything to come. The living planet. Now the Earth is not just a planet of rock, water, and air. It is alive. Its surface hosts colonies of simple cells. Its seas teem with invisible creatures. Its sky is changing with oxygen. Its land is preparing for the day when organisms will crawl, walk, and one day think. Pause for a moment and breathe slowly. Every breath you take is filled with oxygen made by those ancient cells. Every atom of iron in your blood was once dissolved in those early oceans. Every drop of water you drink was once part of those endless rains. You are not separate from this story. You are its continuation. The Earth, born from fire, shaped by impacts, cooled into oceans, restless inside, is now a living world. The first sparks of biology flicker across its surface, tiny lights in a vast darkness. And though billions of years remain before the rise of humans, the path has begun. The Earth has oceans. The Earth has an atmosphere. The Earth has its first simple cells. Billions of years pass in quiet rhythm. Waves crash, storms roll, continents drift. For a long time, nothing seems to change. The oceans remain filled only with invisible single cells. Yet inside them, a slow transformation is underway. A transformation that will turn Earth from a world of microbes into a world of creatures. Breathe slowly. Imagine drifting through those ancient seas. The water is warm, rich with minerals, glowing faintly with sunlight near the surface. At first, you would see nothing, only clear water, no fish, no plants, no animals. But if you could shrink yourself small enough, smaller than dust, you would find an entire invisible universe. Cells of every shape float past, dividing, consuming, growing. They are tiny, but they are countless. And among them, a few begin to experiment with something extraordinary. The birth of complexity. Most of the first cells are simple. They are prokaryotes, tiny sacs of chemistry, without a nucleus, without organelles. They survive well enough, but they remain small. Then, somewhere in those endless oceans, one cell swallows another, not as food, but as a partner. Instead of being digested, the smaller cell lives inside the larger, providing energy, while the larger offers protection. This partnership is the beginning of eukaryotes, complex cells, with internal structures, with nuclei, with mitochondria that generate energy. These cells are far larger, far more capable. They can grow into new shapes, perform new functions, store more information. Imagine it, the first great leap in complexity, born not from competition but from cooperation. Two cells becoming one, and that one becoming the ancestor of every complex organism that will ever exist. Plants, fungi, animals, and humans all trace their lineage to this quiet moment of unity in the sea. Life multiplies. Once eukaryotes appear, the possibilities multiply. For billions of years, they remain microscopic, drifting quietly in the oceans. Yet with complexity comes potential. Some learn to use sunlight more efficiently, building stronger colonies. Some grow larger, stretching their shapes into filaments and sheets. Others develop internal skeletons, shells of calcium, ways to protect themselves. Time stretches forward. The Earth is already over 3 billion years old. Continents shift, mountains rise, seas deepen, the air grows richer in oxygen, thanks to photosynthesis, and then, at last, the long silence breaks. The Cambrian explosion. Around 540 million years ago, Earth enters a new chapter. In a geological blink of time, life explodes in diversity. This is the Cambrian explosion, when complex multicellular organisms suddenly appear in the oceans, filling them with strange and wondrous creatures. Imagine floating in those seas, where once you saw only microbes, you now see shapes unlike anything before. Trilobites crawl across the seafloor, their armored bodies gleaming. Worms tunnel through the mud. Jellyfish drift in the currents, pulsing gently. Sponges grow like towers, filtering water through their pores. Some creatures develop hard shells, protecting them from predators. Others evolve claws, teeth, eyes, ways to hunt. For the first time, there is predator and prey, chase and escape, survival through strategy rather than chance. Life becomes a dance, a struggle, an explosion of possibility. The oceans are alive with color and motion. Tiny shrimps scurry. Strange creatures with spines and fins dart through the water. Some grow enormous compared to their ancestors, stretching several feet long. For the first time, the seas feel crowded, busy, full of energy. The first ecosystems. With diversity comes balance. Algae float near the surface, feeding on sunlight. Small creatures graze on the algae. Larger ones hunt the grazers. Scavengers feed on the dead, returning nutrients to the sea. Predators keep populations in check. The oceans, once quiet, are now an intricate web of life. This is the birth of ecosystems, where life depends on life, where every creature plays a role. The Earth itself feels transformed. For billions of years it hosted only simplicity, but now it holds complexity, interaction, beauty, and struggle. Colonies and communities. Some organisms remain single-celled, but they form colonies. They link together, creating new structures, like the first corals. These colonies build reefs, massive structures that shape the very geography of the oceans. Reefs become homes for countless creatures, sanctuaries of life. On the seafloor, communities form around hydrothermal vents. Even here, in the darkest depths where sunlight never touches, ecosystems thrive. Giant tube worms feed on bacteria. Crabs scuttle between vents. Strange fish glow with bioluminescence. Life has learned to live anywhere, from shallow shores to the deepest trenches, preparing for land. As the oceans teem with new creatures, the continents above wait. For now the land is barren, empty stone and sand, battered by wind, soaked by rain. But the air above is filled with oxygen. The shield of ozone holds strong, and the surface is ready. In time, life will crawl out of the seas, first as plants, then as animals. Forests will rise, insects will swarm, reptiles will roam. But here, in the Cambrian seas, it is only beginning. The Earth has transformed from a lonely sphere into a living planet, bursting with creatures. Breathe deeply now. Imagine yourself drifting through those ancient waters, surrounded by trilobites, by worms, by jellyfish. The sea glows with life, movement, color. This is your ancestry. You are connected not only to the first cells, but to these ancient creatures as well. Their DNA carries forward into yours. Their struggle for survival shaped the world that you inherit. The Earth is alive now, deeply alive. Oceans teem, skies shift, continents prepare, The planet has moved through fire, through water, through chemistry, and now through biology. And yet, the story is still young. The greatest chapters, forests, dinosaurs, mammals, humans, all lie ahead. Life conquers land. The oceans are full now. Creatures crawl across the seabed. Fish dart in currents. Trilobites scuttle like living jewels. The seas are noisy with life, yet above the surface the land remains silent. Bare stone, shifting sands, volcanic ridges, winds whistle across empty plains. Rains fall, rivers carve valleys, but no green softens the grey, no wings stir the air. For billions of years, the land has waited, untouched by life. But that waiting is ending. Slowly, gently, the shore begins to change. The first green. Imagine standing at the edge of an ancient sea, 500 million years ago. The waves crash against rock, and in the spray, tiny green threads cling. These are the first plants, simple algae that have drifted from the sea to the shore. They are fragile, no taller than a fingertip, yet they are pioneers. They soak in sunlight, hold fast to stone, and spread. Over millions of years, these simple algae evolve into mosses and liverworts, spreading across damp ground. The land, once barren, grows patches of green. Small, soft mats cover the rocks, drinking in rain, releasing oxygen into the sky. The earth's face begins to change color. But these early plants are limited. They need constant moisture, hugging shorelines and wetlands. Slowly, evolution gives them new tools: vascular tissue to carry water, roots to anchor in soil, leaves to catch more sunlight. With these gifts, plants grow taller, stronger, bolder. They move inland, away from the safety of the sea. The first forests. Soon the land is no longer bare. Towering ferns and horsetails rise into the air. Lycopods grow as tall as houses, their trunks rough, their fronds spreading wide. The first forests blanket the continents, shading rivers and swamps. Imagine walking among them. No flowers, no grass yet, only towering stems and feathery fronds, a primeval jungle humming with moisture. These forests change everything. Their roots break apart rock, creating the first soils. Their leaves pump oxygen into the air, making the atmosphere richer, more breathable. Their bodies, when they fall, sink into swamps, layering carbon that will one day become coal. The land is alive now, green and growing, reshaping the very surface of the earth. The insect invasion. Where plants go, animals follow. The first to venture onto land are small, armored arthropods, ancestors of insects, spiders and millipedes. At first they crawl through moss and soil, feeding on decaying plants, but soon they grow more diverse. Millipedes as long as cars shuffle through the undergrowth, eating fallen leaves. Dragonflies the size of hawks glide through the air, their wings spanning 2 feet, powered by the oxygen-rich sky. The land, once silent, is now alive with rustling, buzzing, creeping life. Insects pollinate plants. Even before flowers evolve, they scavenge, they hunt, they build, they become the first rulers of the terrestrial world. The leap from water. While insects claim the air and the soil, another great migration begins. In the oceans, fish have grown strong, with bony skeletons and muscular fins. Some fish live in shallow swamps, where the water dries unpredictably. To survive, they evolve lungs, breathing air when gills fail. Their fins grow sturdier, able to push against mud. These are the lobe-finned fish, and from them come the first amphibians. Picture them, half fish, half reptile, with stubby legs, broad heads, and wide mouths. They drag themselves onto land, clumsy but determined. They breathe the air, feed on insects, then return to the water to lay their eggs. This is the first step of vertebrates onto land. the beginning of a journey that will one day lead to reptiles, birds, mammals, and humans. The shoreline is no longer a boundary, it is a bridge. The Carboniferous world. By 350 million years ago, Earth is transformed. Vast swampy forests spread across the continents. Amphibians crawl among the roots, insects swarm the skies, rivers wind through green valleys, oxygen levels climb higher than ever before, fueling giant insects and lush growth. The Earth hums with life, day and night. Plants breathe in carbon dioxide and release oxygen. The air is fresher, the climate warm and humid. This is the Carboniferous period, an age of abundance. Forests stretch for thousands of miles, jungles teeming with creatures. But even in abundance, change is always near. As amphibians thrive, some evolve tougher eggs, covered in shells, so they no longer need to return to the water. These are the first reptiles. Their eggs can survive on dry land, giving them freedom to roam farther, to claim new territories. With this step, life is no longer tied to the sea. The dawn of reptiles. The reptiles spread quickly. They are strong, adaptable, able to live in drier climates where amphibians cannot. Their scales protect them from drying out. Their lungs are more efficient, their limbs more suited to walking. They take over the forests, the swamps, the plains. From these first reptiles will come dinosaurs, crocodiles, turtles, lizards, snakes, birds, and eventually mammals. But for now they are small, simple, unassuming. The true age of reptiles still lies ahead, waiting in the deep future. Close your eyes and breathe slowly. Imagine the land, once barren, now covered in forests. Insects buzz above ferns taller than houses. Amphibians croak from the swamps. Reptiles crawl in the undergrowth, laying their shelled eggs in the soil. The world is loud, alive, green, and wild. The earth has conquered its own emptiness. From oceans to land, from moss to forests, from fish to reptiles, life has spread across the continents. The planet is no longer a silent rock with seas. It is a breathing, growing world. And yet, this is only the middle of the story. Greater creatures are coming. Giants will walk the earth, wings will conquer the skies, and one day intelligence will awaken. But for now, let yourself rest in this forest of the deep past, where the air is rich, the plants are vast, and the earth is alive with its first great symphony of life. The age of dinosaurs. The earth is restless still, continents drift, seas open and close, mountains rise and fall, the forests of ferns and towering trees stretch across the land, while reptiles grow more diverse, more daring. The air is thick with oxygen, the climate warm, the jungles vast. The stage is ready for giants, and soon the world will belong to them. The Triassic dawn. It begins in the Triassic period, about 250 million years ago. The Earth has just endured the greatest extinction it has ever known. Volcanoes have erupted, climates have shifted, oceans have poisoned themselves, and nearly all life has been wiped away. The world is quiet again, scarred and empty. But slowly, life returns. Small reptiles scurry across the land. Amphibians still cling to rivers and swamps. The first mammals, tiny and timid, emerge in the shadows, and among the reptiles, a new lineage appears, the dinosaurs. At first they are small, no larger than dogs, quick-footed hunters and grazers, but they carry within them the potential to grow, to adapt, to rule. Rise of giants. As time flows, the dinosaurs grow larger, stronger, more diverse. The Triassic gives way to the Jurassic, and the land fills with creatures unlike anything before. Long-necked sauropods stretch higher than houses, their tails sweeping across valleys. Stegosaurus, with its plates and spikes, roams the plains grazing on ferns. Fierce predators like Allosaurus stalk the forests, their teeth sharp, their eyes watchful. Picture standing in a Jurassic forest, towering conifers rise above, while herds of sauropods move slowly through the trees, their footsteps shaking the ground. Pterosaurs glide overhead, wings casting shadows across the ferns. The air is humid, heavy with the scent of resin and vegetation. The world feels vast, alive, powerful. Dinosaurs are no longer just animals. They are ecosystems themselves. They graze in herds, defend territories, hunt in packs. They evolve into every shape, every size, from feathered hunters the size of chickens to giants heavier than ships. The Earth is theirs, and they thrive for over 160 million years. A world of change. But the Earth never rests. Continents continue to drift, splitting apart from the supercontinent Pangaea. Oceans widen, climates shift, forests grow, deserts expand, mountains rise. Through it all, dinosaurs adapt. They move into every environment: deserts, swamps, coastlines, forests. Crocodiles rule the rivers, turtles paddle through lakes, and flying reptiles dominate the skies. The first true birds take flight, descendants of small feathered dinosaurs. Insects buzz, pollinating the first flowering plants that begin to spread across the land. Earth is becoming more familiar now, more like the world you know, but still wilder, more primal. Sauropods, the gentle giants. Among the most breathtaking are the sauropods. With necks stretching higher than trees, they graze on the tallest branches, their bodies stretching over 30 meters long. They move slowly, herds of titans, shaking the ground with each step. Their hearts pump enormous volumes of blood. Their lungs fill with air in a rhythm as old as the earth itself. Imagine resting beneath one of these giants as it passes overhead, its shadow swallowing you whole, its breath a slow thunder. They live peacefully, their size their shield. Few predators dare to challenge them. They are the true rulers of their time, gentle giants of a green world. The predators. Yet every world of giants needs its hunters, and in the later Cretaceous period, they arrive in terrifying form. Tyrannosaurus rex, the king of lizards, stalks the land with jaws that can crush bone. Its footsteps echo like drums, its roar shakes the forest, but it is not alone. Raptors, swift and clever, hunt in groups, their claws sharp, their eyes gleaming with intelligence. The balance of life is perfect. Herbivores graze, predators hunt, scavengers feed on the remains, insects recycle the rest. The Earth is a vast web of life, each creature playing its part. A restless planet. Through all of this, the Earth remains restless. Volcanoes erupt, seas rise and fall, climates warm and cool, yet the dinosaurs endure. They thrive for ages longer than humans have even existed, their reign lasting beyond imagination. But no age lasts forever. The planet carries change within it, always, and one day, far into the future, the sky itself will bring an end to the dinosaurs. Breathe. Picture yourself walking through that ancient world. The air warm and heavy, the ground trembling under the footsteps of giants. Pterosaurs glide overhead, dragonflies buzz around ferns, and a herd of sauropods moves slowly across the plain. Somewhere in the distance, a predator roars. The Earth is alive in ways you have never seen, ways you can only imagine. The age of dinosaurs is a symphony of power and beauty, of growth and struggle, of adaptation and survival. For over 160 million years, they ruled without rival, shaping the land, filling the skies, defining an era. Yet already, the seeds of change are in motion. The continents drift, the oceans stir, the skies darken with unseen futures, and though the dinosaurs cannot know it, their time is moving toward an end. The fall of dinosaurs and the rise of mammals. The dinosaurs have ruled for more than 160 million years. They graze in forests, stalk prey across plains, and soar through skies with wings of feather and skin. They have endured the drifting of continents, the rising of mountains, the roaring of volcanoes. They have survived storms, floods, and shifting climates. For so long, it seems they will rule forever. Yet the earth is never still. And sometimes, change comes not in slow centuries, but in a single terrible moment. The sky grows bright. 66 million years ago, the sky above Earth is calm. Sauropods wander across plains. Raptors chase their prey. Tyrannosaurus roams through forests, powerful and untouchable. Then, far above in the emptiness of space, a rock hurtles toward Earth. It is an asteroid, nearly 10 kilometers wide, traveling faster than a bullet. For millions of years it has drifted in silence, but now its path crosses Earth's. The sky flashes. The asteroid enters the atmosphere. In seconds, the air itself ignites. The rock slams into the shallow seas near what is now Mexico, striking with the force of billions of bombs. The world shakes. Waves hundreds of meters high crash outward. Mountains crumble. Forests ignite. The dinosaurs look up, and their age ends. The world in darkness. The impact throws dust, ash, and smoke into the sky. The sun disappears. For months, perhaps years, the earth is shrouded in shadow. Temperatures plummet. Plants wither without sunlight. Herbivores starve. Predators, with no prey, collapse in turn. Forests fall silent. Oceans grow cold. The mighty dinosaurs, who had ruled for ages beyond measure, vanish. But not all life dies. Small creatures endure. Birds, descendants of feathered dinosaurs, take shelter and survive. Tiny mammals, once hidden in the shadows, curled in burrows and nests, endure as well. Insects and seeds, worms and fish, creatures too small to be noticed in the age of giants, now inherit the earth. The age of mammals begins. The mammals had lived quietly through the time of dinosaurs. Small, fur-covered, often nocturnal, they survived by hiding, by eating insects, by staying out of the way, but now the giants are gone. The forests regrow, the sun returns, the earth is warm again, and the mammals begin to rise. They grow larger, braver, more diverse. Some take to the trees, leaping among branches. Others graze across open plains. Some return to the water, swimming through rivers and seas. Within a few million years, they spread across every continent, filling every role once held by reptiles. Imagine early mammals, strange forms unlike anything you know, hoofed creatures with long snouts, small primates scurrying through trees, rodents multiplying quickly, carnivores sharpening their teeth. The earth hums once more with life, new life, smaller but cleverer, faster, more adaptable. A greener world. As mammals rise, the plants change too. During the time of dinosaurs, ferns, conifers, and cycads dominated the land. Now flowering plants spread across the continents. Grass evolves, covering open plains. Forests fill with blossoms. Insects buzz from flower to flower, spreading pollen. The land grows brighter, more colorful, alive with petals and fruit. These plants feed the mammals. The seeds, leaves, fruit, all are eaten and spread by creatures that roam across the land. The earth enters an age of grasslands and forests, buzzing with insects, chirping with birds, rustling with mammals. Giants return. Though the dinosaurs are gone, giants return in new forms. Mammals grow larger and larger. Elephants with tusks roam the savannas. Mammoths, covered in thick fur, march through icy plains. Rhinoceroses the size of houses graze in herds. Whales, descended from land mammals, return to the seas, growing larger than any creature before, even the dinosaurs. Blue whales, born in this lineage, become the largest animals to ever live on Earth. The Earth has not lost its grandeur. It has only changed the cast of characters, the seeds of intelligence. Among these mammals are primates, creatures with grasping hands, keen eyes, and curious minds. They climb trees, live in groups, care for their young. They are not yet human, not yet close, but the seeds of intelligence lie within them. Over millions of years, they will evolve into apes and eventually into humans. But for now, they are only small players in a vast stage. The world belongs to mammals, in all their forms, from tiny shrews to towering mammoths, from bats flying through the night to whales singing in the deep. They rule the Earth now. Take a slow breath. Picture the silence after the asteroid struck. The forests dark, the oceans still. Then imagine the slow return of life, the green spreading across the land, the scurrying of small mammals, the flight of birds across the sky. Out of destruction came renewal. Out of silence came song. The dinosaurs are gone, yet their legacy endures in the birds that sing above you. The mammals rise, filling the earth with new shapes, new sounds, new possibilities. The planet continues to move forward, never stopping, never still. This is the story of resilience. The earth falls into shadow, but life finds a way to continue. The giants vanish, but smaller beings inherit their place. And one day, among those beings will rise a creature who can tell this story, a creature who can look back at the stars, at the earth, and wonder. The rise of humans. The world now belongs to mammals. Forests stretch wide, rivers run deep, grasslands spread like green oceans across continents. Elephants, horses, deer, wolves, and countless others thrive. Birds sing from the trees, insects dance through the air, and whales sing across the seas. The earth has remade itself again, transformed after the fall of the dinosaurs. But among all these creatures, one lineage will take a path unlike any other. From it will come curiosity, memory, stories, and civilizations. From it will come us. It begins with primates, small, tree-dwelling mammals with sharp eyes, grasping hands, and quick minds. They leap from branch to branch, eating fruit, caring for their young, living in groups. Their brains are larger than most, their fingers delicate, their vision keen. Over time, they adapt to many environments. Some remain in trees, others explore the ground. In Africa, in particular, a special story begins. The climate shifts, forests shrink, and wide savannas spread. Some primates climb down from the trees and begin to walk upright. Standing frees their hands to carry food, to shape tools, to hold one another. These early humans are not yet like us, but they are the beginning. They walk across grasslands with stone tools in their hands and fire in their eyes. Walking upright changes everything. It allows them to travel farther, to see danger on the horizon, to free their hands for work. Their brains grow larger, more complex. They learn to shape stones into sharp blades, to use fire for warmth and cooking. Fire becomes their companion, their guardian in the dark. Around flames they gather, share food, and tell the first unspoken stories in gestures and sounds. The world around them changes too. Ice ages come and go, reshaping continents, lowering seas, then raising them again. Glaciers carve valleys, forests shift, grasslands expand. Through it all, early humans adapt. They learn to hunt in groups, to make clothing from animal skins, to build shelters against the cold. Each generation passes its knowledge to the next, and slowly cultures form. From Africa, humans spread outward. They cross deserts, follow rivers, climb mountains. Some reach Asia, others Europe. Still others venture to distant islands. Their footprints scatter across the globe. They encounter new climates, new animals, new challenges, and they adapt to them all. Their brains grow ever more capable, their languages richer, their tools sharper. In time, they learn to shape the land itself. They plant seeds, domesticate animals, and begin farming. Villages appear, then towns, then cities. Civilizations rise along rivers, the Nile, the Tigris and Euphrates, the Indus, the Yellow River. With farming comes surplus, with surplus comes writing, with writing comes history. The earth, which once was only fire and stone, now carries the weight of memory. Human beings tell stories of gods and stars, of oceans and mountains, of beginnings and endings. They build temples, pyramids, walls and roads. They carve their presence into the planet itself. Yet even now, beneath their feet, the earth is restless. Continents still drift, volcanoes still erupt, storms still rage. The planet remains alive, older than all its inhabitants, patient and eternal, and the humans, though powerful, are only the newest chapter in a story billions of years old. The earth today and tomorrow. The earth has travelled through fire, through oceans, through forests, through giants, through extinctions, through rebirth, and now it is here, in this moment, carrying you upon its surface. Look around you in your mind's eye. The forests are green, the rivers shimmer, the mountains rise like guardians, the deserts spread like seas of sand, the oceans breathe with tides. It is the same earth that was once a ball of fire, that once was only rain, that once was ruled by dinosaurs. Yet now it carries cities, languages, cultures, and you. Today, the earth is alive in ways more complex than ever. Billions of humans live upon its land, shaping it, farming it, building upon it. The sky is crossed by birds, but also by airplanes. The seas are filled with fish, but also with ships. The forests are home to ancient trees, but also to villages and roads. The earth is no longer just nature. It is nature and humanity entwined. Breathe slowly and imagine the planet as a whole, seen from space, a blue marble, wrapped in white clouds, continents painted in green and brown, oceans glowing with deep sapphire. It spins silently in the black of space, yet upon its surface, life never stops moving. This is the only world you know, the only cradle of life in a vast cosmos. Every breath you take is a gift from its atmosphere. Every sip of water is a drop from its endless cycle. Every meal is sunlight transformed into food by plants that root themselves in its soil. The earth has given you everything. Yet the earth is also fragile. Its climate shifts. Its forests are cut. Its oceans warm. Its air fills with smoke. Humans have grown powerful enough to shape the balance of the planet itself. The choices made today ripple forward into tomorrow. The earth listens quietly, as it always has, holding both resilience and vulnerability within its skin. But do not imagine this as despair. The earth has always changed and always endured. It has survived impacts, fire, ice, and extinction. It holds the memory of all that has lived, and it continues to turn, patient as ever. What matters now is awareness. Awareness that you are not apart from the planet, but part of it. Its soil is in your bones, its air in your lungs, its water in your blood. You and the earth are not separate stories. You are the same story. Think of the future. Perhaps forests will regrow. Perhaps rivers will run cleaner. Perhaps humans will learn once again to live not above the earth but within it, as its children. Or perhaps storms will grow stronger, seas higher, deserts wider. The future is not written. It waits, just as the oceans once waited for life, just as the skies once waited for oxygen. It waits for what you choose. Close your eyes and imagine Earth in millions of years. The continents will shift again. Mountains will rise where seas now lie. Deserts will become oceans, and oceans will dry into valleys. The stars above will shift. The sun will slowly grow warmer, changing the climate of the world. And yet, through all of this, the Earth will continue its patient journey around the sun, spinning in the silence of space. And farther still, billions of years from now, the sun itself will change. It will swell into a red giant, its heat consuming the Earth. The oceans will boil, the air will vanish, the crust will melt again into fire. The Earth, born from stardust, will return to stardust once more. But even then, its story will not truly end. For every atom that makes up the planet will drift into space to become part of something new. A star, a comet, another world, perhaps another Earth. Breathe gently and let this thought settle. You are alive in this moment, on a planet that has passed through fire and ocean, through dinosaurs and extinctions, through forests and cities, to reach this very night. You are part of its story, and it is part of yours. When you sleep upon its crust. When you breathe its air. When you dream within its orbit. The Earth is ancient yet young, fragile yet resilient, fierce yet nurturing. It carries all that has been and all that will be. And tonight, as you drift towards sleep, it holds you gently, as it has held life for billions of years. Let your body rest. Let your mind soften. Let the story of Earth continue around you, patient and eternal. For the planet turns, the stars shine, and tomorrow will rise as surely as the first dawn ever did.